Look up at the night sky. What do you see? Pinpricks of light, distant suns, the gentle glow of the Milky Way. It's a familiar, almost comforting sight. But what if I told you that this cosmic tapestry, this grand display of stars and galaxies, might all be built upon a foundation of something far stranger, far darker? What if the very first objects to emerge from the fiery dawn of the universe weren't stars at all, but something infinitely more mysterious and powerful? Imagine a cosmos so young that not a single star had yet ignited, a realm of pure, searing energy. And in that chaos, the first true structures to form weren't beacons of light, but perfect knots of absolute darkness. We're talking about the universe's very first black holes, entities that might have been born not from dying stars, but from the raw turbulence of creation itself. These are primordial black holes, and their potential existence rewrites the first chapter of everything. The idea is as profound as it is thrilling. We're used to thinking of black holes as the end result of a star's dramatic collapse, the final sigh of a stellar giant. But primordial black holes, or PBH, are a completely different kind of beast. Theorized to have sprung into existence in the first fleeting fractions of a second after the Big Bang, they are hypothetical relics from a time before time, as we know it, had even settled down. They wouldn't be the children of stars, they would be their predecessors, their ancient ancestors. This means these phantom giants could be lurking anywhere in the voids between galaxies, within our own solar system, or even comprising the very dark matter that holds the cosmos together. Their story is the ultimate cold case file of astrophysics, a mystery buried 14 billion years deep, and that mystery is exactly what we're diving into today. We are about to embark on a journey through 30 of the most fascinating, mind-bending theories surrounding these cosmic pioneers. We'll explore how a universe still in its infancy could have given birth to such monstrous objects, what they might be made of, and how they could have secretly shaped the evolution of everything we see. From the tiniest, atom-sized black holes that evaporate in a flash of radiation, to colossal ones that could serve as the seeds for the supermassive black holes sleeping at the hearts of galaxies today. This isn't just a list of facts, it's a frontier of modern science, a playground for the imagination where the most fundamental laws of physics are put to the ultimate test. So get ready to question everything you thought you knew about the beginning, because we are about to peer into the darkness that came before the light. To understand how such an incredible event could even be possible, we need to rewind the cosmic clock all the way back to the very beginning, to a time that defies all intuition. Picture the universe not as a vast expanse of stars and galaxies, but as a searingly hot, unimaginably dense soup of energy and fundamental particles. This was the primordial cosmos, less than a second old. In this frantic, chaotic environment, the pressure and temperature were so extreme that matter and energy were constantly converting into one another. Now, according to Einstein's theory of general relativity, energy and mass are two sides of the same coin. This means that in that ultra-dense early universe, the sheer concentration of energy itself could warp the fabric of space-time. The key idea behind the Big Bang direct collapse theory is that this infant universe wasn't perfectly smooth. It had tiny wrinkles, slight variations in density. Think of a pot of water just as it begins to boil, with some areas bubbling more vigorously than others. These ripples in the cosmic soup are known as density fluctuations. Most of these fluctuations were minor, but the theory suggests that some regions might have been exceptionally dense. If a particular patch of space was packed with enough energy mass, its own gravitational pull would have become overwhelming. In the rest of the universe, the outward pressure from the intense heat and radiation was fighting against gravity's inward crush. But in these ultra-dense pockets, gravity would have won the battle instantly and catastrophically. There would have been no time for a star to form, no gradual process of accumulation. the region would have simply collapsed directly in on itself, punching a hole through the fabric of space-time and creating a black hole from pure, raw energy. This is what makes them primordial. They are literally as old as the universe itself, formed from its initial, most violent impulses. The scale of these black holes would have been determined by the size of the collapsing region. A small, particularly dense knot might have created a black hole with the mass of an asteroid, while a larger, overdense region could have collapsed into something with the mass of 1,000 suns or even far more. This is a crucial point. Unlike stellar black holes, which have a minimum mass limit set by the death of large stars, primordial black holes could theoretically come in any size. They could be smaller than a single atom or larger than a supermassive black hole. Their mass wasn't tied to stellar processes, it was tied to the random clumpiness of the newborn cosmos. This makes them true fossils, frozen relics that carry information about the conditions of the universe in its very first second of existence. Finding one would be like holding a perfectly preserved sample of creation itself, a direct window into a time before the first starlight ever shone. But the Big Bang direct collapse isn't the only way to cook up a primordial black hole. To find another potential recipe, we have to consider an even more bizarre chapter in the universe's infancy, the era of cosmic inflation. This theory proposes that a fraction of a second after the Big Bang, the universe underwent a growth spurt of almost unimaginable speed, expanding exponentially from a subatomic speck to something macroscopic in a dizzyingly short time. Now, one compelling idea suggests that the end of this inflationary period might have been just chaotic enough to forge black holes. Think of the cosmos during inflation not as a single, smooth entity, but as a frothing sea of spacetime itself. Different regions of this sea might have undergone what physicists call a phase transition, cooling and settling down at slightly different times, like water freezing into ice in patches. Each of these patches would become its own distinct bubble universe, with our observable cosmos being just one bubble among potentially countless others. As inflation ended, these bubbles of stable spacetime would have begun to collide and merge with each other. Picture two soap bubbles gently bumping into one another. When they meet, the energy concentrated at the point of collision is tremendous. Now, scale that idea up to a cosmic level. The collision between two of these infant universe bubbles would have been a cataclysmic event, releasing an extraordinary concentration of energy into a very small area. This sudden, intense injection of energy could have warped the local fabric of spacetime so severely that it triggered a gravitational collapse, instantly forming a black hole. In this scenario, the black hole isn't born from the collapse of matter, but from the sheer violence of spacetime itself rearranging its fundamental structure. These black holes would be like scars left over from the moment our cosmic bubble first made contact with its neighbors. What's truly fascinating about this theory is the incredible range of masses these collision-born black holes could possess. The size and energy of the colliding bubbles would determine whether the resulting black hole was microscopic, asteroid-sized, or perhaps even as massive as those we find at the centers of galaxies today. This provides a potential solution to one of astronomy's biggest puzzles. How did supermassive black holes grow so large so quickly? We observe these behemoths weighing billions of times the mass of our Sun in galaxies that existed when the universe was less than 1 billion years old. It's incredibly difficult for a star-born black hole to accumulate that much mass in such a short time. But if some of these early galaxies were seeded by primordial black holes already weighing thousands of solar masses from the very beginning, perhaps created in a colossal bubble collision, they would have had a massive head start, a ready-made foundation upon which to grow. This theory elegantly connects the largest-scale physics, the inflationary dynamics of the entire universe, directly to the formation of specific, powerful objects that would go on to dictate the evolution of the first galaxies. If the inflationary bubble collisions seem like a dramatic birth for a black hole, Then our third theory ventures into the realm of the truly exotic. This idea takes us to a moment when the universe was not just expanding, but fundamentally changing state, much like steam condensing into water or water freezing into ice. In its earliest, hottest moments, the universe is thought to have been a place of perfect symmetry, where the fundamental forces we know today, electromagnetism, the strong and weak nuclear forces, were unified into a single super force. But as the cosmos expanded and cooled, it underwent a series of radical shifts. These weren't just temperature drops, they were cosmic phase transitions, moments when the underlying symmetry of the universe broke, and the forces we recognize began to peel apart from one another. Now, when any substance undergoes a phase transition, the process isn't always perfectly smooth. Think about what happens when a lake freezes on a cold night. The ice doesn't form a single, flawless crystal across the entire surface at once. Instead, it starts in many different places simultaneously. As these individual patches of ice grow, they eventually meet. But their crystalline structures don't always align perfectly. Where they collide, you get a flaw in the ice, a crack, a seam, a boundary where the structure is stressed and disordered. The early universe is theorized to have behaved in a strikingly similar way. As it cooled and its symmetry broke, different regions of space may have chosen different stable states, just like different patches of ice crystallize in slightly different orientations. The consequences of this imperfect cosmic freezing are mind-bending. The boundaries where these different domains met wouldn't be simple cracks, they would be defects woven into the very fabric of spacetime itself. Physicists have given these hypothetical structures names like cosmic strings, which are unimaginably dense, one-dimensional cracks in reality, or domain walls, two-dimensional surfaces that contain immense energy density. These aren't made of matter, they are topological kinks, wrinkles in the geometry of the cosmos that were frozen in place during its rapid cooling. And just like a flaw in a crystal can be a point of weakness, these cosmic defects could have become the seeds for creation. If a cosmic string, for instance, developed a kink or a loop, or if several domain walls intersected, the concentration of energy at that point could have been so extreme that the gravitational field became overwhelming. The defect would have collapsed under its own intense gravity, instantly pinching off a piece of spacetime to form a black hole. In this scenario, primordial black holes aren't born from collapsing matter or energy, but from the snapping of a cosmic flaw, a scar left over from the moment the universe's fundamental forces took their modern forms. This theory suggests that the black holes dotting our cosmos could be the fossilized remnants of the universe's own messy adolescence, permanent markers of its transition from a state of perfect symmetry to the complex, structured reality we inhabit today. This brings us to one of the most profound and far-reaching possibilities in all of modern cosmology, a theory so elegant it could solve two of the universe's greatest mysteries with a single dark entity. We've been searching for the identity of dark matter for decades, knowing it makes up about 85% of all the matter in the cosmos, yet it remains completely invisible, detectable only by its gravitational pull on galaxies and light. The leading candidates have been exotic, hypothetical particles like WIMP, or weakly interacting massive particles. But what if the answer isn't a swarm of unseen subatomic particles, but a vast population of ancient celestial ghosts? This is the daring proposition that primordial black holes are the dark matter. Think about the defining properties of dark matter. It must be massive enough to exert a strong gravitational influence. It must not interact with light, making it perfectly dark, and it must be stable enough to have persisted for the entire history of the universe. Primordial black holes, especially those within a certain mass range, fit this description almost perfectly. A black hole, by its very nature, is the ultimate dark object. It emits no light of its own, its gravitational presence is its only signature, and if they formed in the first instance after the Big Bang, they have been around since the beginning, silently weaving the cosmic web. The elegance is stunning. The very same objects that could have seeded the first galaxies might also be the invisible scaffolding that holds them together. The key to this theory lies in the mass. For primordial black holes to constitute all of dark matter, they couldn't be too small or too large. If they were extremely tiny, say the mass of an asteroid or smaller, they would have evaporated away by now due to Hawking radiation, a process where black holes slowly lose mass. If they were too massive, each one would weigh as much as 1,000 suns or more. While that's possible, we would expect to see more direct evidence of their gravitational effects, like frequent distortions of starlight as they passed between us and other stars, an effect called gravitational microlensing. The most promising window, the sweet spot, is thought to be for black holes with masses comparable to a large asteroid or even a planet. A vast, unseen population of these mountain-to-planet-sized black holes, drifting like icebergs in the dark ocean between stars, could collectively generate the exact gravitational pull we attribute to dark matter without producing the telltale signs that would make them easy to spot. This idea creates a fascinating contrast with the search for particle-based dark matter. For years, physicists have built incredibly sensitive detectors deep underground, hoping to catch the faintest bump from a WIMP. It's a search for the incredibly small. The primordial black hole hypothesis, on the other hand, shifts the search into the realm of celestial objects. Instead of looking for subatomic interactions, we would look for their subtle gravitational effects on the fabric of space itself. This is already happening through projects that monitor millions of stars for the fleeting brightening caused by a dark object passing in front of them. The fact that we haven't found a large population of these lensing events has actually helped to rule out certain mass ranges for primordial black holes as the sole component of dark matter, sharpening the search. It may be that dark matter is a mixture, a cosmic cocktail of different entities, with primordial black holes playing a significant role alongside other, yet-to-be-discovered particles. The possibility remains open that these ancient relics are not just a footnote in cosmic history, but the dominant form of matter in the universe, the hidden architects of the cosmos we see today. While the theories of their formation are captivating, they all lead to a fundamental question. If primordial black holes are out there, what should we be looking for? What would one of these ancient relics actually weigh? This brings us to a cornerstone of the entire field, a pivotal piece of theoretical work that gave the search for PBHs its scientific backbone. It's known as the Kerr-Hawking mass spectrum, named after the physicists Bernard Kerr and the legendary Stephen Hawking. Their work in the 1970s provided the first rigorous mathematical framework for understanding the possible sizes of these objects, and it all comes down to a simple yet profound connection. The age of the universe at the moment of a black hole's birth directly determines its mass. To grasp this, we need to visualize the early universe not as static but as rapidly evolving. In the first second after the Big Bang, the cosmos was expanding at a furious rate. Now imagine a region of space that has just become dense enough to collapse into a black hole. The size of that region is critically important, but here's the key. The size of a region that can collapse is not arbitrary. It's limited by the distance light could have traveled in the age of the universe up to that point. This is called the horizon distance. Think of it as a cosmic communication limit. In a universe that is 1 second old, no information, no influence can have traveled farther than 1 light second. Therefore, a patch of space that collapses to form a black hole at that 1 second mark can be no larger than 1 light second across. This scale sets the mass. The mass of the resulting black hole is simply the amount of mass energy that was contained within that horizon-sized volume at the moment of collapse. And because the density of the universe was astronomically higher in the past, this leads to a fascinating inverse relationship. A black hole that forms incredibly early, say when the universe was only a tiny fraction of a second old, collapses from a very small region. But because the density at that time was so unimaginably high, that small volume still contains a tremendous amount of mass energy, resulting in a relatively low mass black hole. As the universe ages, even by microseconds, it expands and becomes less dense. So, a region collapsing a little later will be larger in physical size, but because the density has dropped, the total mass inside might be similar, or could even be larger for later times depending on the precise dynamics. Carr and Hawking's calculations showed that PBHs could form across a vast range of masses, from the microscopic to the supermassive, with each mass corresponding to a specific, precise moment in the thermal history of the young cosmos. This theoretical prediction creates a powerful spectrum, a menu of possible primordial black holes. On one end, you have black holes that formed when the universe was around 1 Planck time old, an almost incomprehensibly brief interval. These would have been true quantum black holes with a mass of about 20 micrograms, the weight of a tiny grain of sand, but compressed into a volume smaller than a single proton. On the other end of the spectrum, if a PBH formed when the universe was about 1 second old, its mass could be as large as 100,000 times that of our Sun. This mass spectrum is not just a theoretical curiosity, it's a practical guide for astronomers. It tells us that we shouldn't just be looking for one type of black hole. Our search must be broad, scanning the skies for evidence of objects across this entire mass range, each one a fossilized timestamp from a different instant after creation. The power of the Carr-Hawking spectrum is that it links the abstract physics of the first second directly to potential observations we could make today. For instance, it makes a definitive prediction about the very smallest black holes. Those minuscule Planck mass black holes would have been so hot due to Hawking radiation that they would have evaporated their entire mass away in a final, explosive burst of particles almost immediately after forming. They are long gone, but a black hole with the mass of a small asteroid forming a little later would have a much lower temperature and a lifetime longer than the current age of the universe. According to the spectrum, such objects should still be with us, drifting silently through the galaxy. This directly informs the search for dark matter, focusing efforts on specific mass windows. Furthermore, the spectrum suggests that if PBHs formed in abundance, we might expect to see a whole population of black holes within a certain mass range, rather than a random distribution. Not finding them where the spectrum predicts they should be is just as important as finding them, as it helps us rule out specific models of the early universe. In this way, the Carr-Hawking work transformed the hunt for primordial black holes from a speculative guess into a targeted scientific investigation, providing a crucial map for navigating the darkness. But what if the very first black holes weren't primordial at all in the strictest sense? What if they were, instead, the spectacular tombstones of the very first stars? This theory takes us from the abstract violence of the early universe to the fiery, more familiar drama of stellar death, but with a scale and intensity we can barely comprehend. To explore this, we must introduce a truly legendary generation of stars, population 3. Astronomers classify stars into populations based on their metal content, with metals meaning any element heavier than hydrogen and helium. Our Sun, for example, is a population 1 star rich in these heavier elements. Population 2 stars are older and much more metal poor, but population 3 stars are the mythical ancestors, the true pioneers. They are hypothesized to have been the very first stars to ever ignite, forming from the pristine, unpolluted gas of the early universe, a cosmic fuel composed of only hydrogen, helium, and a trace of lithium. With no heavier elements to help cool the gas clouds, these first stars couldn't form in small, modest sizes. Instead, they were forced to coalesce into true behemoths. The scale of these stars is almost beyond imagination. Current models suggest a typical population 3 star could have been anywhere from 100 to over 1,000 times more massive than our Sun. They would have burned with a ferocious, brilliant blue-white intensity, living fast and dying young. While a star like our Sun has a lifespan of billions of years, these colossal giants would have blazed through their nuclear fuel in just a few million years, a mere cosmic heartbeat. Their deaths would have been correspondingly apocalyptic. When such an immense star reaches the end of its life, the outward pressure from nuclear fusion can no longer hold back the crushing weight of its own gravity. The core collapses catastrophically. For the very largest of these population 3 stars, this collapse might not even result in a traditional supernova explosion. Instead, the entire star could simply vanish, collapsing directly into a black hole without a significant blast, as if the universe itself had swallowed it whole. For slightly less massive stars, the death would be a hypernova or a pair instability supernova, an explosion so violent it would briefly outshine an entire galaxy, leaving behind a black hole as its final, defiant signature. This creates a crucial distinction that helps clarify the entire search for the first black holes. The black holes born from population 3 stars are fundamentally different from primordial black holes. Primordial black holes, as we've discussed, are true children of the Big Bang, formed from density fluctuations or cosmic defects before any stars existed. They are primary creations. The black holes from population 3 stars, however, are secondary. They are the end products of stellar evolution, just like the black holes we are familiar with today. The key difference is one of timing and ancestry. These would be the first stellar mass black holes forged in the furnaces of the very first stars. So when we ask, what were the universe's first black holes? We are really asking 2 separate questions. Were they the ancient, primordial ones that may have seeded the growth of everything? Or were they the powerful remnants of the first generation of stars that finally brought light to the cosmos? This theory offers a compelling and dramatic alternative, suggesting that the first light and the first darkness might have been born in the very same fleeting moments. This brings us directly to one of the most compelling arguments for the existence of primordial black holes, a theory that attempts to solve a cosmic timing problem so severe it has kept astronomers awake at night. Scattered across the universe, we find the most massive objects known to exist, supermassive black holes. These are not the stellar mass black holes formed from dying stars. These are true leviathans, weighing millions or even billions of times the mass of our Sun. And here is the puzzle. We have observed them in galaxies that existed when the universe was less than 1 billion years old. That's an incredibly short time on the cosmic scale. To put it in perspective, growing 1 billion solar mass black hole in under 1 billion years is like trying to grow a giant sequoia tree in a single week, and the natural processes we understand simply don't operate fast enough. If a supermassive black hole started its life as a mere stellar mass black hole, say 10 or 20 times the Sun's mass, the process of growth is accretion, pulling in vast amounts of gas and dust. But this process has a speed limit known as the Eddington limit. It's a balancing act. As matter falls into a black hole, it releases an enormous amount of energy in the form of radiation. This radiation pushes outward, and if it becomes too intense, it can actually blow the surrounding gas away, shutting off the black hole's own food supply. A stellar mass black hole can only consume material so quickly. To reach supermassive status in just a few 100 million years, a black hole would have to consistently accrete material at or even above this theoretical limit for its entire existence, which seems highly improbable. It's a race against time that, according to standard models, these objects simply shouldn't have won. This is where primordial black holes offer an elegant and powerful solution. Imagine if, at the dawn of time, the universe didn't just produce tiny black holes, but also a population of what we call intermediate mass black holes. These would be the cosmic heavyweights with masses ranging from a few hundred to several 100,000 times that of our Sun. Now, if one of these primordial intermediate mass black holes happened to be sitting at the center of a collapsing cloud of gas that would become one of the first galaxies, it would have a colossal head start. Instead of starting from scratch with 10 solar masses, it begins the race with 1,000 or even 10,000. The difference is dramatic. A more massive seed has a stronger gravitational pull, allowing it to draw in gas from a wider area more effectively. It also has a higher Eddington limit, meaning it can consume matter at a much faster rate without choking itself off. What was an impossible sprint for a small black hole becomes a manageable, steady marathon for a massive primordial seed. This theory elegantly bridges the gap between the infant universe and the mature cosmos we observe. These primordial seeds would act as gravitational anchors around which the first protogalaxies could coalesce. The black hole and its host galaxy would then grow together in a symbiotic relationship, a feedback loop where the galaxy feeds the black hole, and the black hole's intense energy output regulates the galaxy's star formation. The existence of such seeds would neatly explain the presence of fully formed supermassive black holes in the very earliest galaxies we can detect. They are not anomalies, they are the expected outcome of a universe that planted massive dark seeds in its fertile youth. This idea transforms primordial black holes from mere theoretical curiosities into potential master architects, whose initial gravitational imprint directly guided the formation of the largest structures in the universe, shaping the cosmic landscape we inhabit today. And this brings us to a concept so revolutionary it overturned a fundamental assumption about black holes, a prediction that forever links their ultimate fate to the quantum weirdness of the subatomic world. For a long time, the classical view of a black hole was simple and grim. Things fall in, but nothing, not even light, ever comes out. They were considered perfect one-way streets into oblivion. But in the 1970s, Stephen Hawking performed a breathtaking feat of theoretical physics by marrying Einstein's theory of gravity with the strange rules of quantum mechanics. His conclusion was startling. Black holes are not entirely black. They can, in fact, emit radiation. They can slowly, imperceptibly evaporate. This phenomenon, now known as Hawking radiation, has profound and specific consequences for the entire population of primordial black holes. To grasp how this works, we need to venture into the realm of quantum physics. Empty space, according to quantum theory, is not truly empty. It's a seething, bubbling foam of virtual particles. These are particle-antiparticle pairs that spontaneously pop into existence from the energy of the vacuum, borrowing energy from nowhere for an incredibly brief moment before annihilating each other and vanishing back into nothingness, paying back the energy loan. This happens everywhere all the time. Now, imagine this quantum frenzy occurring right at the edge of a black hole's event horizon, the point of no return. Hawking realized that if this particle-antiparticle pair appears right at the boundary, a bizarre theft can occur. One particle might fall across the event horizon, forever lost to the black hole while its partner escapes into space. From the perspective of an outside observer, the black hole has just emitted a particle, but there's a catch. To conserve energy, the particle that fell in must have had negative energy. This means the black hole itself loses a tiny, tiny amount of mass in the process. It's as if the black hole has paid the energy loan for the escaped particle with a fragment of its own mass. This process is incredibly slow for a large black hole. A typical stellar mass black hole has such a weak Hawking radiation effect that it would take far, far longer than the current age of the universe to lose any appreciable amount of mass. But here's the critical link to primordial black holes. The rate of evaporation is inversely related to the black hole's mass. The smaller the black hole, the more intense the Hawking radiation. This is because a smaller black hole has a much stronger gravitational gradient at its tiny event horizon, making it easier for these quantum thefts to occur. For a primordial black hole, size is everything when it comes to its lifespan. A PBH with the mass of a mountain would be incredibly hot by astronomical standards, glowing with Hawking radiation and evaporating on a timescale comparable to the age of the universe. But a PBH with a mass less than that, say, the mass of a large asteroid or smaller, would have a much higher temperature and a much shorter life. In fact, any primordial black hole that started its life with a mass less than about that of 1 billion metric tons would have completely evaporated by now. Their existence would have been a fleeting cosmic spark. This leads to a fascinating possibility for detection. The final moments of a small, evaporating black hole would not be a quiet fizzle. As the black hole loses mass, it gets hotter, which makes it evaporate faster, which makes it hotter still. This creates a runaway process. In the last second of its life, the black hole would release the energy equivalent of a 1 megaton hydrogen bomb in a tremendous burst of high-energy particles and gamma rays. It would be a spectacular final shout of existence. This means that even if the vast majority of small primordial black holes have long since vanished, we might still be able to find evidence of their ancient deaths. Astronomers are actively searching the sky for these unique gamma-ray bursts. They wouldn't look like typical supernova explosions or gamma-ray bursts from colliding neutron stars. They would be much shorter and have a distinct energy signature. Finding such an event would be like discovering the fossilized echo of a black hole that blinked out of existence millions of years ago, providing indirect but powerful proof that these objects were once a real part of our cosmic history. The hunt for these final explosions turns the evaporation process from a theoretical curiosity into a potential observational tool, allowing us to probe the universe for ghosts of black holes that are no longer there. Now, let's turn from the silent evaporation of the smallest black holes to the opposite end of the spectrum, the cosmic crashes of the largest ones. If primordial black holes are indeed out there, some of them are likely bound together in binary pairs, locked in a gravitational dance that inevitably ends in a spectacular merger. And when they collide, they don't just vanish, they ring the very fabric of spacetime itself like a bell, sending out ripples known as gravitational waves. This gives us a potential channel for discovery that doesn't rely on light, but on sensing the distortions in space. The key, however, is that the gravitational waves from merging primordial black holes would tell a very different story than the ones we've already detected. Consider what we've observed so far with observatories like LIGO and Virgo. These incredible instruments have opened a new window on the universe by detecting gravitational waves from the mergers of stellar mass black holes, typically weighing between about 5 and 100 times the mass of our Sun. These are the end products of massive stars. Their merger signals have a specific signature, a characteristic chirp that rises in frequency and amplitude as the black holes spiral inward. The masses involved fit neatly within our understanding of stellar evolution. But what if a future detection revealed a merger between two black holes, each with a mass of, say, 30 times that of our Sun? That alone would be exciting, but not necessarily extraordinary. The real clue would be if those black holes were found to be merging in a region of space where there are no stars, far away from any galaxy. How could a binary pair of stellar black holes form in the emptiness of intergalactic space? It would be incredibly difficult according to our current models of stellar formation and binary evolution. This is precisely the kind of anomalous event that would make astronomers sit up and take notice, pointing strongly towards a primordial origin. The difference lies in their formation history. A binary pair of stellar black holes starts its life as a binary pair of massive stars. They are born together, evolve together, and eventually collapse into black holes that remain gravitationally bound. Their story is tied to the star-forming regions of galaxies. Primordial black hole binaries, on the other hand, would have a much more ancient and exotic origin. In the dense, crowded environment of the very early universe, two PBHs passing relatively close to each other could have become gravitationally captured. As the universe expanded, they would be left orbiting each other in complete isolation, a lonely couple drifting through the dark for billions of years, their orbits slowly decaying until they finally merge. A merger detected in the vast void between galaxies would be a powerful, almost undeniable fingerprint of a primordial pair. To truly unlock this mystery, we need a new generation of observatories. While LIGO and Virgo are exquisitely sensitive to the high-frequency waves from stellar mass collisions, the mergers of much more massive black holes like the intermediate mass seeds we discussed earlier produce gravitational waves at lower frequencies. This is where a mission like LISA, the Laser Interferometer Space Antenna, comes in. Planned for launch in the next decade, LISA will consist of 3 spacecraft flying in a giant triangle millions of kilometers apart, forming a gravitational wave observatory in space. Its design is perfect for detecting the low-frequency hum of mergers involving black holes weighing thousands or even millions of solar masses. If the early universe produced a population of these heavier primordial black holes, LISA would be the instrument to hear their collisions. It could reveal a cosmic chorus of mergers from the dawn of time, a background rumble of gravitational waves completely distinct from the signal produced by stellar remnants. Finding such a population would not just confirm the existence of primordial black holes, it would allow us to census them, to understand their mass range and distribution, painting a detailed picture of the conditions that spawned them in the first fraction of a second of everything. So, if gravitational wave observatories are listening for the distant crashes of these ancient objects, how do we search for the ones that are simply drifting in silence? The answer lies in one of Einstein's most fascinating predictions, a phenomenon that turns the entire universe into a vast, natural magnifying glass. This technique is called gravitational microlensing, and it's arguably our most powerful tool for hunting solitary primordial black holes across the galaxy. The principle is beautiful in its simplicity. According to general relativity, mass curves the fabric of spacetime. Light, traveling along this curved geometry, doesn't follow a straight line, it bends. Now imagine a dark, compact object like a primordial black hole drifting through the void. If this object happens to pass almost directly between Earth and a distant background star, something remarkable happens. The black hole's gravitational field acts as a tiny lens, warping the space around it and focusing the light from that faraway star. From our perspective, the star doesn't just get slightly brighter, it can undergo a sharp, temporary increase in brightness, a flash that can last from a few hours to several months, depending on the mass of the lensing object and its speed. This signal is incredibly distinctive. Unlike a variable star that pulses in a regular pattern, a microlensing event is a single, symmetric spike in brightness. The light curve rises smoothly to a peak as the black hole aligns most perfectly with the star and then fades away in an identical manner. The duration of this brightening is the critical clue. A more massive lensing object will have a wider region of gravitational influence, causing a longer-lasting event. If the flash is very short, just a few hours, it could point to a small planet mass object. An event lasting weeks or months would suggest something much heavier, perhaps a black hole with the mass of a star. This allows surveys to not just detect dark objects, but to effectively weigh them. For primordial black holes, this is a perfect hunting method. We don't need them to be accreting matter or emitting any radiation, we only need their gravity. They betray their presence by the brief, ghostly imprint they leave on the light of a background sun. This search is not just theoretical, it's a massive, ongoing astronomical endeavor. Projects like the Optical Gravitational Lensing Experiment, or OGLE, based in Chile, and the Hyper-Subprime CAM, or HSC, survey on the Subaru telescope in Hawaii have been at the forefront of this detective work for years. They don't look at a few stars at a time, they monitor hundreds of millions of stars night after night, often focusing on dense stellar fields like the bulge of our own Milky Way galaxy or the Large Magellanic Cloud. The goal is to catch these fleeting flashes of amplified light. The sheer volume of data is staggering, and the analysis relies on sophisticated software to sift through the measurements, identifying the unique signature of a microlensing event among all the other reasons a star's brightness might fluctuate. It's a cosmic version of finding a needle in a haystack, except the needle is invisible, and we only know it's there by the way it briefly illuminates a single piece of straw. The results from these painstaking searches have been both illuminating and surprisingly restrictive. While many microlensing events have been detected, the vast majority can be explained by more mundane objects, faint, low-mass stars, brown dwarfs, or even free-floating planets. The key question is, how many of these events defy explanation by normal astrophysical objects and could therefore be attributed to primordial black holes? The answer so far is very few, if any. This absence of evidence is itself a powerful form of evidence. It has allowed scientists to effectively rule out the possibility that primordial black holes within a specific mass range, roughly from the mass of our Moon up to about the mass of our Sun, could make up all or even a significant fraction of the dark matter in our galaxy. If the dark halo of the Milky Way were teeming with planet-sized or asteroid-sized black holes, these sensitive surveys would have seen thousands of unexplained microlensing events. The fact that they haven't tells us that such a population, if it exists, must be far sparser than once hoped. This doesn't mean the hunt is over, it means it's become more refined. The constraints placed by microlensing surveys have narrowed the field, pushing the most promising mass windows for primordial black holes as dark matter to either much smaller or much larger scales. It's a perfect example of how a null result in science can be just as valuable as a positive detection. By telling us where primordial black holes are probably not, these surveys guide theorists and observers to focus their efforts on the remaining possibilities, making the ongoing search for these cosmic phantoms more targeted and precise than ever before. But what if we could turn existing cosmic objects into giant, natural detectors, specifically designed to catch a passing primordial black hole? This brings us to a truly wild and ingenious theory that involves two of the most extreme objects in the universe, the ancient ghost of a PBH and the incredibly dense corpse of a dead star, a neutron star. The idea is that if a primordial black hole, especially one on the smaller end of the mass spectrum, were to collide with or be captured by a neutron star, the resulting interaction wouldn't be a subtle gravitational nudge. It would be a catastrophic and potentially observable event, a cosmic demolition from the inside out. To understand why this is such a compelling scenario, we need to appreciate the unique nature of a neutron star. These are the remnants of supernova explosions, stars so dense that a single teaspoon of their material would weigh billions of tons on Earth. They are essentially giant atomic nuclei, city-sized spheres packed with neutrons, held up against their own immense gravity by a quantum mechanical force called degeneracy pressure. They are incredibly robust, but imagine a primordial black hole, perhaps with the mass of a small asteroid or even a planet, on a trajectory that takes it directly through a neutron star. Because the black hole is so compact, it would pass through the outer layers of the star with little resistance. However, once inside, the situation changes dramatically. The black hole would immediately begin to accrete material. It would start eating the neutron star from within. The process is as horrifying as it is fascinating. Safe inside the body of the star, shielded from the outside universe, the black hole would be sitting in an all-you-can-eat buffet of ultra-dense matter. It would pull material from the neutron star's core, and as this matter spirals into the black hole, it would be compressed and heated to incredible temperatures, releasing a torrent of radiation, particularly high-energy X-rays and gamma rays. This is where the theory gets its predictive power. For a brief period, the neutron star might appear to transform into an entirely new kind of object. Instead of emitting the steady, predictable radio pulses of a pulsar, or the more moderate X-ray signature of an accreting neutron star in a binary system, it would flare with an intense and unique internal energy source. Astronomers might see a star that suddenly, and without any other explanation, begins to shine with an unprecedented luminosity in high-energy light, a brilliance powered by its own consumption. The end game of this internal feast is even more dramatic. As the black hole consumes more and more of the neutron star, it grows in mass. A more massive black hole has a stronger gravitational pull, which allows it to accrete material even faster. This creates a runaway feedback loop. The black hole devours the star from the inside, eventually consuming so much of its core that the star can no longer support its own structure. The entire neutron star would collapse inward, vanishing entirely into the black hole in a final, swift act. From our distant vantage point, this might look like a pulsar whose clockwork regular signals suddenly and permanently cuts off. One day, the star is there, ticking away. The next, it has been erased from the sky, replaced by a silent, slightly more massive black hole. This sudden disappearance of a known neutron star would be a profound and shocking event, a clear signature of an internal cataclysm with very few other plausible explanations. This theory effectively turns every neutron star in the galaxy into a potential PBH trap. The vast distances between stars make a direct collision incredibly rare, but given enough time and a large enough population of neutron stars, it becomes a statistical possibility. The hunt, therefore, involves meticulous monitoring. Astronomers keep a close watch on known pulsars and neutron stars, looking for any that exhibit these strange, internal energy flares, or more dramatically, any that simply vanish. While no such event has been conclusively observed yet, the mere possibility adds a thrilling dimension to the study of these dense stellar remnants. It means that every time we observe a neutron star behaving strangely, we have to consider the fantastical possibility that it might be hosting a primordial black hole in its core, a relic from the dawn of time that is now finishing a meal 14 billion years in the making. Now, let's shift our focus from the silent drift of larger black holes to the spectacular deaths of the smallest ones, and how their final moments might have left a permanent mark on the oldest light we can see. We've talked about how Hawking radiation causes small primordial black holes to evaporate, ending in a violent burst of energy. But what happens if you scale that idea up, not to a single black hole, but to a hypothetical population of billions or even trillions of them evaporating throughout the early cosmos? The collective energy released would be staggering, and according to this theory, it would have poured into the universe, subtly heating the surrounding gas and potentially imprinting itself on the very first light emitted after the Big Bang, the cosmic microwave background, or CMB. To understand this, we need to picture the universe when it was just a few 100,000 years old. At this point, it was a hot, dense plasma of protons, electrons, and light. Photons couldn't travel freely. They were constantly bouncing off the free electrons, trapped in a swirling fog. Then, as the universe expanded and cooled, a pivotal event occurred known as recombination. Protons and electrons combined to form neutral hydrogen atoms. Suddenly, the fog cleared. The photons, which had been trapped, were finally set free to travel across the universe. This first flash of liberated light is what we detect today as the cosmic microwave background, a faint glow that fills all of space. It's a baby picture of the universe, and its properties, like its temperature and tiny fluctuations, are exquisitely measured. Now, imagine if during this crucial period, or even earlier, the cosmos was also filled with a background hum of high-energy radiation from countless evaporating primordial black holes. This extra energy would have interacted with the cosmic plasma, leaving a potential fingerprint on the CMB that we might still be able to detect. The primary way this could happen is through a process called spectral distortion. The CMB has an almost perfect blackbody spectrum, meaning its intensity at different frequencies follows a very specific, smooth curve predicted by fundamental physics. However, if a significant amount of energy was injected into the cosmic plasma after the universe was about 1 year old but before recombination, that perfect blackbody spectrum would have been subtly altered. The evaporating black holes would have dumped energy primarily in the form of photons and other particles into the universe. This extra energy would have heated the electrons in the plasma, which in turn would have slightly changed the way those electrons scattered the CMB photons. The result wouldn't be a dramatic change, but a tiny, specific distortion of that perfect blackbody curve. It would be like a faint brushstroke of extra color painted over the cosmic canvas. This gives cosmologists a powerful tool. By using space-based observatories like the Planck satellite to measure the CMB spectrum with incredible precision, they can search for any deviations from the perfect blackbody shape. The fact that we see almost no distortion places very tight constraints on how much energy could have been released by processes like PBH evaporation during that specific window of time. In other words, the remarkable smoothness of the CMB spectrum tells us that there could not have been a large population of small primordial black holes evaporating at that particular cosmic epoch. If there had been, we would see the evidence in the light. This is another example of how a non-detection is actually a profound discovery, effectively ruling out certain models of the early universe. But the story doesn't end with the microwave background. Another potential signature lies in a different part of the electromagnetic spectrum, the cosmic infrared background. This is a diffuse glow of infrared light that permeates the universe, coming from the cumulative emission of all dusty galaxies and stars throughout cosmic history. However, there appears to be a slight excess in this background, a bit more infrared light than can be easily accounted for by known sources. One intriguing proposal is that this extra glow could be the accumulated light from the final bursts of the very smallest primordial black holes that evaporated much later, long after the CMB was set. While the energy from an individual evaporation event would be long gone, the combined infrared light from all such events across cosmic time could, in theory, contribute to this background glow. Pinpointing this contribution is incredibly challenging, as it requires untangling the signal from the light of countless galaxies, but it remains a fascinating possibility for future, more sensitive infrared telescopes. By studying both the microwave and infrared backgrounds, we are effectively conducting a forensic investigation of the universe's energy budget, searching for the faint, lingering echo of a population of ancient black holes that flickered out of existence, leaving only their radiation as a testament to their brief, dramatic lives. What if the most distant and mysterious objects in our own cosmic backyard aren't made of rock and ice at all, but are instead frozen chunks of space-time? This leads us to a truly speculative but captivating idea: that some of the asteroids and dwarf planets lurking in the cold, dark reaches of our solar system, particularly in the Kuiper belt and the distant Oort cloud, might actually be primordial black holes in disguise. Imagine a primordial black hole with a mass comparable to a large asteroid or even a planet like Earth. Its gravitational pull would be identical to that of a solid object of the same mass, but its physical size would be unimaginably small. A black hole with the mass of Earth, for instance, would be compressed into a sphere less than 2 centimeters across. To any distant observer, this object wouldn't emit or reflect light. It would be a perfect point of darkness, detectable only by its gravity. If such an object were captured by the Sun's gravity and settled into a distant orbit, our telescopes would see absolutely nothing. We would only infer its presence by the way it tugs on other bodies, making it a phantom planet, a ghost in the orbital machinery of our solar system. The implications for their density and behavior are staggering. A traditional asteroid or planet has a limit to its density, constrained by the atomic structure of matter. Even the densest elements, like osmium, can only be packed so tightly. A primordial black hole, however, represents the ultimate state of density. This extreme compactness has fascinating consequences. If a small asteroid mass PBH were to pass through a regular asteroid or a comet, the interaction would be unlike any collision between solid bodies. The black hole, being so tiny, would simply pass through the object, leaving a microscopic, needle-like tunnel. However, its immense gravity would tear at the rock or ice as it passed, generating intense internal heat through tidal forces. This could potentially cause the asteroid to fracture or even exhibit sudden, unexplained outgassing, as if it were a comet that mysteriously activated without approaching the Sun. The hunt for such anomalies is already part of astronomy, but this theory gives them a thrilling new potential cause. So, how could we actually test this incredible idea? The answer lies in meticulous gravitational detective work. While we cannot see these potential dark interlopers directly, we can map the solar system's gravity field with exquisite precision by tracking the orbits of everything within it. Every planet, moon, asteroid, and comet follows a path dictated by the Sun's gravity and the subtle pulls of all other masses. If there is an unseen mass, a phantom planet that is actually a primordial black hole, orbiting out in the Kuiper belt or the Oort cloud, its gravitational influence would reveal itself by causing tiny, unexplained deviations in the orbits of known objects. We might see a cluster of distant Kuiper belt objects whose paths are ever so slightly perturbed, all pointing towards a common, invisible source of gravity. This is precisely how Neptune was discovered in the 19th century, by analyzing anomalies in the orbit of Uranus. Today, we have the technology to detect gravitational perturbations on a much finer scale. This is where missions like New Horizons become potential PBH hunters. After its historic flyby of Pluto, New Horizons continues its journey into the Kuiper belt. Its precise trajectory is tracked by NASA, a deep space network with incredible accuracy. If the spacecraft were to experience an unexpected, tiny change in its velocity, a slight gravitational nudge that cannot be accounted for by the known bodies in the solar system, it would set off alarm bells for astronomers. Such an anomalous acceleration could be the signature of a close encounter with an unseen mass. Of course, any such signal would have to be rigorously scrutinized to rule out other causes, like the gentle pressure of the solar wind or tiny outgassing from the spacecraft itself. But a persistent, unexplained tug would be a tantalizing clue. Future, dedicated missions could be designed specifically as gravitational mappers, sent on paths that crisscross the outer solar system to create a detailed gravity map, searching for the hidden footprints of these dark planets. Finding one would not just rewrite the inventory of our solar system. It would mean that a relic from the universe's first second has been hiding in plain sight, orbiting our Sun all along. Now, let's consider a different kind of signal, one that doesn't come from gravity or light, but from a hail of high-energy particles constantly bombarding our atmosphere from the depths of space. For over a century, scientists have been detecting cosmic rays, protons, atomic nuclei, and other subatomic particles traveling at nearly the speed of time. Their origins are a major puzzle. Some come from the Sun or supernova remnants, but the very highest energy cosmic rays carry millions of times more energy than anything we can produce in particle accelerators on Earth. What cosmic engines could possibly launch particles with such ferocious power? One compelling, if speculative, answer points directly to the dying moments of the smallest primordial black holes. The connection lies in the final, feverish stage of Hawking radiation. As we've discussed, a very small black hole evaporates faster and faster, growing hotter until it effectively explodes. In its last fraction of a second, it doesn't just emit a gentle glow. It becomes a particle accelerator in its own right, firing off a tremendous burst of high-energy gamma rays, neutrinos, protons, and antimatter particles like positrons and antiprotons. This isn't a slow leak, it's a catastrophic detonation. The energy spectrum of this final burst is predicted to be very broad, meaning it would produce particles across a wide range of energies, potentially including those at the extreme high end that have baffled astronomers for so long. The theory proposes that what we classify as mysterious ultra-high-energy cosmic rays might not be particles being accelerated by a distant object, but could instead be the final death screams of primordial black holes evaporating in our galactic vicinity. To test this idea, we need to think about distribution and timing. If this theory is correct, we wouldn't expect these high-energy particle bursts to come from any specific direction, like a known star or galaxy. Primordial black holes, if they are a component of dark matter, would be scattered throughout the galactic halo, a vast spherical cloud enveloping the Milky Way. Their deaths would be random events popping off like firecrackers at unpredictable locations all around us. This matches one of the key observational mysteries. The highest energy cosmic rays appear to arrive from all directions equally. They seem to be isotropic. Furthermore, the event itself would be incredibly brief. The final burst of a PBH is over in a flash, meaning the flash of particles would be a one-time event, not a continuous source. This fits with the fact that we don't see repeating sources for these ultra-high-energy events. However, this elegant theory faces significant challenges. The primary obstacle is the sheer energy required. For a primordial black hole's final burst to produce particles with the energies we observe, the black hole itself would need to have a very specific mass, one that causes it to evaporate at precisely the right temperature to generate such powerful emissions. Moreover, to account for the observed flux of these rare cosmic rays, there would need to be a sufficient number of these small PBHs reaching the end of their lives within a detectable distance of Earth. If the population is too sparse, the events would be so rare that we'd be incredibly lucky to detect one. On the other hand, if the population were dense enough to produce a frequent shower of high-energy particles, it might conflict with other constraints, like the precise measurements of the cosmic gamma-ray background. The absence of a clear, smoking gun signal in existing data has led many physicists to conclude that while evaporating PBHs might contribute to the cosmic ray background, they are unlikely to be the dominant source for the very highest energy events. Yet, the search continues with sophisticated detectors like the Pierre Auger Observatory constantly analyzing the showers of particles created when cosmic rays hit our atmosphere, searching for any unique signature that could point back to a black hole's final quantum mechanical scream. This tendency of dark matter to clump isn't just a large-scale phenomenon. It operates on every level, down to the very smallest structures that gravity can possibly build. If the dark matter is indeed made of primordial black holes, then this clustering takes on a fascinating new dimension. Instead of a perfectly smooth, ghostly fog, the dark matter halo of a galaxy like our Milky Way would be more like a rich, chunky stew filled with dense knots and lumps. This is the theory of PBH dark matter mini-halos. Due to their immense mass concentrated in a microscopic volume, primordial black holes would have a powerful gravitational influence from the very beginning. In the early universe, even the slightest overdensity would act as a gravitational seed. Ordinary dark matter particles, if they exist, would be drawn to these seeds, but so would other primordial black holes. A single PBH would start to attract a cloud of other PBHs and any other dark matter around it, forming a tight, localized cluster, a mini-halo within the larger galactic halo. The scale of these mini-halos could vary dramatically. A cluster might contain just a handful of asteroid-mass black holes, or it could grow to encompass thousands of them, collectively weighing as much as a star. These wouldn't be static structures either. As they orbit through the galaxy, they would interact with each other, sometimes merging, sometimes being torn apart by tidal forces. Think of it as an invisible, dynamic ecosystem of dark matter clumps, all moving through and shaping the galaxy in ways that a perfectly smooth distribution of dark matter would not. This has direct consequences for the visible matter we can see. For instance, consider a globular cluster, a dense ball of hundreds of thousands of ancient stars orbiting the galactic center. If one of these dark mini-halos were to pass through such a cluster, its concentrated gravitational pull would give the stars a slight jolt. It wouldn't tear the cluster apart, but it could subtly perturb the orbits of the stars, perhaps even flinging a few out into the galactic halo. Astronomers sometimes observe faint streams of stars trailing from these clusters, which are often interpreted as evidence of past interactions with other visible objects. But some of these features could potentially be the ghostly fingerprints of a passing dark matter clump, a swarm of primordial black holes that left no other trace. Perhaps the most promising way to detect these hidden structures is by watching how they bend the fabric of spacetime itself. We've discussed microlensing of individual stars, but we can scale this idea up to probe the existence of entire mini-halos. The targets for this are some of the brightest and most distant objects in the universe, quasars. These are the intensely luminous cores of active galaxies, powered by supermassive black holes devouring matter. When the light from a distant quasar travels across billions of light years to reach us, its path can be warped by the gravitational influence of all the mass it encounters along the way. If a PBH mini-halo, a clump of dark matter with the total mass of a dwarf galaxy but concentrated into a much smaller volume, were to drift through the line of sight, it would act as a powerful gravitational lens. However, instead of causing a single, sharp brightening like a lone black hole would, the complex structure of a mini-halo would create a more intricate pattern. It could produce multiple, distorted images of the quasar, or cause subtle, correlated flickers in its brightness over time as different parts of the mini-halo pass in front of it. Analyzing these complex lensing signatures is an emerging frontier in astronomy. It requires monitoring quasars for years, even decades, to build up a detailed map of their light variations. The challenge is immense, as many other factors can cause a quasar to flicker, but sophisticated computer models can simulate what the lensing effect of a dark matter mini-halo should look like, providing a specific pattern to search for in the data. Finding a clear match would be monumental. It would not only provide strong evidence for the existence of primordial black holes, but would also reveal the hidden architecture of dark matter, showing us that it is not a simple, smooth veil, but a complex, hierarchical structure built from the ground up, with ancient black holes serving as the foundational stone. Now we venture beyond the familiar forces of gravity and into the quantum realm, where the rules of reality become strange and new particles flicker in and out of existence. This theory suggests that the first black holes might not have been born from the clumping of regular matter or energy, but from the collapse of something far more exotic, hypothetical particles predicted by a fascinating framework known as supersymmetry. To understand this, we need to briefly step into the world of particle physics. Supersymmetry, often called SUSY for short, is a theoretical concept that proposes a profound and elegant symmetry in nature. For every known fundamental particle we've discovered, like electrons and quarks, there should exist a much heavier, undiscovered superpartner. This idea isn't just for mathematical beauty. It could solve several major puzzles in physics, including the nature of dark matter. One particularly intriguing prediction of some supersymmetric models is the existence of a strange, stable object called a cue ball. Imagine a cue ball not as a literal ball, but as a coherent, soliton-like lump of a new kind of field, a condensate of squarks and leptons, the superpartners of the familiar quarks and electrons. Unlike ordinary matter, which is held together by forces like the strong nuclear interaction, a cue ball is a non-topological soliton, meaning it's a stable, localized concentration of energy that maintains its form. Think of it as a droplet of an exotic quantum fluid, a tiny island of supersymmetry that could have survived the frantic early moments of the cosmos. Because of their unique properties, these cue balls could have been produced in vast numbers during the high-energy conditions just after the Big Bang. And crucially, some types of cue balls could have been absolutely stable, persisting long after other particles had annihilated or decayed. Here's where the connection to black holes becomes spectacular. These cue balls wouldn't just sit there idly. They would carry a tremendous amount of mass energy packed into a very small volume. If conditions were right, these exotic particles could have attracted one another, clumping together through their gravitational pull. As a cluster of cue balls grew denser and more massive, its collective gravity would intensify. Eventually, a critical threshold would be crossed. The gravitational pull at the center of this accumulating mass of exotic matter would become so overwhelming that not even the unique quantum forces holding the cue balls apart could resist it. The entire cluster would undergo a catastrophic gravitational collapse. There would be no supernova, no stellar drama, just a silent, direct implosion as this lump of supersymmetric matter punched a hole straight through space-time, instantly creating a black hole. In this scenario, a black hole is born not from a star's death, but from the sudden collapse of a stable state of exotic particle physics. This theory provides a breathtaking bridge between the very small and the very large. It directly links the quest to understand the fundamental building blocks of the universe at the highest energies with the appearance of the most massive astrophysical objects we observe. A primordial black hole formed in this way would be a fossil, but not just a fossil of density fluctuations. It would be a frozen relic from the era when supersymmetric particles roamed freely through the cosmos. Finding evidence for such a black hole would indirectly validate the existence of supersymmetry itself, offering a cosmic clue to a theory that has so far eluded our largest particle colliders. It suggests that the answers to some of our deepest questions in particle physics might not be found in underground tunnels on Earth, but by looking out into the vastness of space and studying the dark shadows left over from the universe's first moments. And this brings us to a critical and dynamic chapter in the life story of these ancient objects, the formation of binary pairs. We've been considering primordial black holes largely as solitary drifters, but the early universe was an incredibly dense and crowded place. In such an environment, encounters were not just possible, they were inevitable. This theory explores how two PBHs forming in close proximity could have become locked in a gravitational dance that spanned the entire age of the cosmos, a dance whose final moments we might now be able to witness. The process begins not with a dramatic collision, but with a subtle, inescapable pull. In the hot, dense plasma of the infant universe, imagine two regions that are both dense enough to collapse directly into black holes. If these two regions are close enough together, separated by a distance not vastly greater than their own individual sizes, their gravitational destinies become intertwined from the moment of their birth. The key factor here is the expansion of the universe itself. As the cosmos rapidly inflates and then continues to expand, it tries to pull these two newborn black holes apart. But if their mutual gravitational attraction is stronger than the overall expansion rate at that very early time, they successfully resist being separated. They become gravitationally bound to each other. Now, they aren't initially on a direct collision course. They each have some small, random velocity relative to the surrounding medium. This gives the pair a slight angular momentum, meaning instead of falling straight into one another, they begin to orbit a common center of mass. They form a binary system. What's fascinating is that this binary is effectively frozen in time almost immediately. As the universe continues to expand at an accelerating rate, the distance between this binary pair and any other PBHs or large masses increases enormously. The binary is left in pristine isolation, a closed system of two dark objects orbiting each other in the vast emptiness, with no other significant gravitational influences to disturb them for billions of years. The likelihood of this happening and the resulting properties of the binary depend heavily on two main factors: The first is the initial average separation between PBHs when they form. If PBHs were very common, forming a dense cluster in the early universe, then the typical distance between any two neighboring black holes would be small, making gravitational capture and binary formation a frequent occurrence. If, however, PBHs were relatively rare, sprinkled sparsely throughout the cosmos, then most would have been born too far apart to ever become bound, destined to drift alone forever. The second critical factor is the initial density of the surrounding universe. In the earliest moments, the universe was filled with a dense, uniform plasma of radiation and matter. This ambient medium exerts a drag known as dynamical friction on the moving black holes. This drag actually helps to stabilize a newly formed binary, sapping away any excess energy and helping to circularize their orbit, setting them on a long, stable path. The initial mass of the black holes also plays a role. More massive PBHs have a stronger gravitational reach, making it easier for them to capture a partner from a greater initial distance. The fate of these primordial binaries is a slow, inexorable spiral. Even in the near-perfect vacuum of space, they don't orbit forever unchanged. They lose energy over astronomical timescales through the emission of gravitational waves. As the two black holes orbit each other, they ripples in spacetime that carry energy away from the system. This causes their orbit to gradually decay. They spiral closer and closer together, orbiting faster and faster until they finally merge in a violent collision that shakes the fabric of the cosmos. The merger rate of these binaries today is not just a minor detail, it's a cornerstone prediction of any PBH model. If a significant fraction of dark matter is made of primordial black holes, and if they frequently formed binaries in the early universe, then the rate at which we should detect their mergers with gravitational wave observatories like LIGO and Virgo becomes a specific, calculable number. This turns astronomy into a powerful testing ground. By counting the number of black hole mergers we detect and measuring their masses, we can compare the observed rate against the predicted rate from PBH binary models. A higher than expected rate of mergers involving black holes in a specific mass range, especially if those black holes appear to have formed in isolation far from other stars, would be a compelling piece of evidence pointing towards a primordial origin, suggesting that the cosmos is echoing with the final embraces of couples that found each other in the first second of time. But just as we grapple with the timing of the first supermassive black holes, a new and even more startling puzzle has emerged from the deepest images ever taken, courtesy of the James Webb Space Telescope. This theory connects primordial black holes directly to one of JWST's most head-scratching discoveries, the existence of fully formed, massive galaxies at distances, and thus times that were previously thought impossible. We're seeing galaxies that look surprisingly mature with vast populations of stars in a universe that was only a few 100 million years old. It's as if we've found a sophisticated, bustling city in what we believed was a barren wilderness just after the last ice age. The standard model of galaxy formation, which relies on the gradual accumulation of gas and the slower pace of star formation, struggles to explain how these cosmic metropolises built themselves up so quickly. There simply doesn't seem to have been enough time for gravity to work its usual patient magic. This is where the gravitational prowess of primordial black holes offers another compelling solution, acting as a cosmic catalyst for rapid growth. Imagine the early universe as a vast, dark, and relatively smooth sea of hydrogen and helium gas. For a galaxy to form, you need a seed, a gravitational nucleus to trigger the collapse of a gas cloud. In the standard picture, this seed is a slight overdensity of dark matter, a gentle ripple that slowly gathers more matter over hundreds of millions of years. But if you swap that gentle ripple for a powerful, pre-existing gravitational anchor, like a primordial black hole with the mass of 1,000 suns, the entire process is supercharged. A PBHc doesn't just gently pull, it creates a deep, immediate gravitational well. Gas flowing into this well would fall inward at tremendous speeds, colliding and shock heating, which in turn triggers an explosive burst of star formation far more efficiently and rapidly than normal. The presence of such a massive seed would fundamentally alter the timeline. Instead of a slow, steady build-up, galaxy formation becomes a dramatic, fast-paced event. A primordial black hole sitting at the center of a collapsing gas cloud would act like a gravitational vacuum cleaner, drawing in material from a much wider area than a comparable mass of star-like dark matter ever could. This intense accretion wouldn't just build the central black hole, it would create a ferocious environment where stars are forged at a staggering rate, a phenomenon astronomers call starburst activity. The galaxy that results would be massive, luminous, and mature, looking in a very short period, neatly matching the surprising characteristics of the high redshift galaxies JWST has revealed. In this scenario, these distant giants aren't puzzling anomalies. They are the expected outcome of a universe that got a massive head start by planting ultra-dense seeds in its infancy. Furthermore, this theory provides a beautiful, synergistic link between the growth of the black hole and the growth of its host galaxy from the very beginning. In later epochs, we see evidence of this co-evolution, where supermassive black holes and their galaxies seem to grow in lockstep. But for the JWST galaxies, this relationship would have been established at birth. The primordial black hole and the nascent galaxy would have grown together in a powerful feedback loop from day one. The energy and radiation from the rapidly accreting black hole could have both fueled star formation by compressing gas clouds and also regulated it by eventually blowing away excess gas, preventing the galaxy from growing uncontrollably. This inherent balance could explain not only how these galaxies grew so big so fast, but also why they appear so well structured and mature, rather than being chaotic, unregulated firestorms. The existence of a ready-made, massive gravitational engine at the center of these early protogalaxies solves the dual mystery of rapid growth and early maturity, painting a picture where the first lights in the universe were not faint candles, but brilliant beacons ignited by the deep, dark wells of primordial black holes. But what if the very idea of a black hole's central point of infinite density, the singularity, is not the final word? What if, instead of a one-way ticket to oblivion, matter reaching the center of these objects experiences something far more extraordinary? This brings us to a theory that emerges not from classical cosmology, but from a leading candidate for a theory of quantum gravity, and it proposes a radical alternative for the fate of matter within a black hole, one that could fundamentally reshape our understanding of the universe's first dark objects. It's called the theory of Planck stars. To appreciate this idea, we need to confront the great unfinished business of modern physics, the clash between Einstein's general relativity and quantum mechanics. General relativity gives us our best description of gravity on large scales, predicting that matter collapsing under its own weight will continue indefinitely, crushing down to an infinitely dense point, the singularity. But physicists are nearly unanimous in believing this is a sign that the theory breaks down. Infinite density isn't physically possible. It's a mathematical artifact signaling that we need a deeper theory, one that incorporates the quantum nature of spacetime itself. Loop quantum gravity is one such attempt. It proposes that spacetime is not a smooth, continuous fabric, but is instead woven from tiny, discrete loops, a fundamental pixelation of reality at the smallest possible scale, the Planck scale. This granular structure has a profound consequence. It introduces a repulsive force that emerges at extremely high densities. Think of it like this: you can only compress a material so far. Once you try to pack atoms into a space smaller than the atoms themselves, you encounter immense resistance. In loop quantum gravity, spacetime itself behaves this way. As matter collapses towards what would have been a singularity, the quantum gravitational repulsion becomes overwhelmingly powerful. Instead of collapsing to a point, the collapsing matter hits a quantum bounce. It's as if the star that formed the black hole, or the primordial energy that collapsed, reaches a maximum density and then rebounds like a ball bouncing off an ultra-dense floor. The result isn't a singularity, but a super-dense, hot, fleeting object, a Planck star. It would be a ball of matter existing for only a fraction of a second, but crammed with the entire mass of the black hole into a volume not much larger than an atom. Now apply this breathtaking concept to the very first black holes. If primordial black holes formed in the early universe, they might not have been the eternal prisons described by classical physics. Instead, they could have been the universe's first Planck stars. Imagine a primordial black hole forming from a dense fluctuation in the first second. It would have immediately begun its life cycle of collapse, but according to this theory, it would have very quickly, within a tiny fraction of a second, reached its maximum density and bounced. The entire process of collapse and bounce would be hidden behind the event horizon, the point of no return for light. To an outside observer, it would still look like a black hole. But on the inside, a brief, ferocious firestorm of a Planck star would have flashed into existence and then begun to expand. This leads to an even more staggering possibility connected to the idea of a bouncing cosmology. Some models suggest that if our entire universe could undergo a big crunch, collapsing under its own gravity, the same quantum repulsion could cause it to bounce back, leading to a new Big Bang. A Planck star inside a black hole is like a miniature, localized version of this cosmic cycle. The interior of a black hole could be a separate, baby universe born from the bounce of its parent star. For a primordial Planck star, this means the universe's first black holes might not have been in points, but rather cosmic wombs. Each one could have given birth to a new space-time domain, a new universe with its own physical laws branching off from our own. In this mind-bending view, our entire cosmos might itself be the interior of a black hole formed in a parent universe, and the primordial black holes within it could be the seeds for an infinite fractal of future universes. While this remains highly speculative, it demonstrates how rethinking the nature of the first black holes doesn't just change their story. It has the potential to rewrite the very narrative of cosmic origins, linking the smallest quantum grains of space-time to the grandest possible structures in the multiverse. Now we turn our attention to a specific class of cosmic object that has long eluded astronomers, a missing link in the black hole family tree that could be the key to unlocking the primordial mystery. These are the intermediate mass black holes, or IMBHs. We are quite familiar with the two extremes, stellar mass black holes, born from dying stars and weighing up to about 100 times our Sun, and the supermassive behemoths that dominate galactic centers, tipping the scales at millions or even billions of solar masses. But what about the vast middle ground? For decades, evidence for black holes with masses between 1,000 and 100,000 solar masses was scarce and hotly debated. They were the cosmic equivalents of Bigfoot, hinted at but never definitively confirmed. This gap is more than just a curiosity. It represents a crucial evolutionary step. How does a universe go from creating small, stellar mass holes to building the supermassive monsters we see so early on? The prevailing idea was that supermassive black holes grew by gradually merging with smaller ones and accreting gas, a process that should have left behind a population of intermediate mass objects as stepping stones. Yet finding them has proven incredibly difficult. This is where the primordial black hole theory offers an elegant and powerful explanation. What if intermediate mass black holes aren't the products of later mergers and growth at all? What if they are, instead, the original seeds themselves, formed fully fledged in the first instance of the cosmos? Imagine a primordial black hole born not as a tiny speck, but as a true heavyweight from the very beginning. According to the Hawking mass spectrum we discussed, a PBH forming when the universe was around 1/10 of a second old could easily possess a mass of several thousand suns. This object would be an intermediate mass black hole from its very birth. It wouldn't need to slowly accumulate mass over billions of years. It started its life already in the intermediate range. This elegantly sidesteps the difficult problem of building such an object through stellar processes alone, which is a slow and inefficient affair. The elusiveness of PBHs, which once seemed like a problem for the theory, actually becomes one of its strongest supporting arguments. If these objects are primordial, they wouldn't necessarily be found where we typically look for black holes. A stellar mass black hole is often located in a binary system with a visible star, its presence given away by X-rays as it pulls material from its companion. A supermassive black hole is impossible to miss, sitting in the bright, active core of a galaxy. But a primordial intermediate mass black hole, especially one that has not been able to pull in a significant amount of gas and dust, would be effectively dark and silent. It could be drifting alone in the void between stars, or perhaps lurking at the center of a small, faint globular cluster, its gravitational influence subtle and difficult to distinguish from the collective pull of thousands of stars. Their quiet nature is exactly what we would expect from ancient fossils that have largely avoided dramatic interactions. Recent breakthroughs are making this theory more compelling than ever. The field was revolutionized in 2019 with the first confirmed detection of an intermediate mass black hole, thanks to gravitational wave astronomy. The LIGO and Virgo observatories detected a signal named GW190521 from the merger of two black holes. The incredible part was the mass of the resulting object, about 150 solar masses. This placed it squarely in the intermediate mass range, but even more telling were the masses of the two black holes that collided, 85 and 66 solar masses. These are far heavier than any stellar mass black hole we thought could form from a single star. How did two such massive black holes come to merge, especially in a region of space where there weren't enough stars to explain their formation? A primordial origin provides a clean answer. These could have been two primordial black holes that formed a binary pair in the early universe and spent billions of years spiraling toward their final collision. This single event didn't just discover a new class of black hole. It provided a tantalizing clue that the cosmos might be populated with ancient, massive black holes that have no stellar explanation. Finding more of these intermediate mass objects is therefore one of the most active pursuits in modern astronomy. The search is multi-pronged. Scientists are scouring dense star clusters, looking for the telltale high-speed orbits of stars around an unseen, massive central object. They are also searching for the faint X-ray glow that might be produced if one of these black holes occasionally captures and devours a stray star or a cloud of gas. But the most promising technique may once again be gravitational waves. The future LIS Space Observatory will be perfectly tuned to detect the mergers of black holes in the intermediate mass range from a few hundred to a few 100,000 solar masses. If LIS detects a significant population of these mergers, it will provide a census of these elusive objects. A high rate of such events would be incredibly difficult to explain through standard stellar evolution alone, but it would be a natural consequence of a universe that was seeded with a population of primordial intermediate mass black holes from the very beginning. Each detection brings us closer to confirming that these missing links are not missing at all, but are instead the silent, ancient architects that have been hiding in plain sight all along. While we often picture black holes as ultimate destroyers, consuming everything in their path, this next theory offers a radical shift in perspective. It suggests that these primordial objects might not have been agents of darkness, but rather the very midwives of light. Imagine the universe again in its infancy, a vast, dark, and relatively uniform expanse of cooling hydrogen and helium gas. For the first stars to ignite, this gas needed to collapse under its own gravity, but it faced a problem. Without heavier elements to help radiate away heat, and without significant initial density variations, this collapse could have been a slow and inefficient process. Enter the primordial black hole. Drifting silently through this cosmic gloom, a PBH would have been a concentrated point of immense gravity. As it moved through a primordial gas cloud, it wouldn't just passively drift. Its gravitational pull would have acted like a plow, gathering and compressing the gas ahead of it. Think of it as a gravitational snowplow clearing a street, but instead of pushing snow aside, it's piling up the very raw material of creation. This compression is the critical first step. By squeezing the gas, the black hole dramatically increases its local density and pressure. In regions that might have otherwise remained diffuse for much longer, the PBH's passage creates a shock wave of overdensity. The gas behind this shock front becomes unstable, reaching a threshold where its own self-gravity can overcome the internal pressure and any residual heat. This triggered collapse could initiate the process of star formation on a vastly accelerated timeline. Instead of waiting for random fluctuations to slowly build up over eons, the first protostellar cores could have been jump-started by the gravitational nudge of a passing dark giant. In this scenario, a single primordial black hole could have seeded not just one, but an entire trail of star-forming regions along its path through the cosmic gas, like a celestial gardener planting seeds of light in the dark soil of the early universe. This theory elegantly addresses a key challenge in understanding the first stars, known as population 3 stars. We believe these stars were enormous, but how such behemoths could coalesce so quickly has been a puzzle. A primordial black hole provides a natural mechanism for gathering the tremendous amounts of gas required. The gravitational well of even a modest-sized PBH would be far deeper and more focused than that of a simple gas cloud. It could efficiently draw in enough material to form a stellar giant hundreds of times more massive than our Sun. Furthermore, the dynamics are fascinating. In some cases, the star might form around the black hole itself, with the PBH acting as a kernel around which the star accretes. In other scenarios, the black hole might simply trigger the collapse and then move on, leaving behind a dense core that would continue to collapse into a star on its own. This paints a picture where the first darkness and the first light are not adversaries, but partners in cosmic evolution, with the gravitational influence of the former directly enabling the birth of the latter. The implications of this positive feedback are profound. If PBHs were abundant enough, their catalyzing effect could have led to an earlier and more widespread era of star formation than would have otherwise occurred. This could help explain why we see evidence of early galaxies and enriched elements, the products of stellar life and death, so soon after the Big Bang. The universe may have lit up faster because it was filled with these invisible gravitational triggers. This theory transforms our view of primordial black holes from mere cosmic predators into potential benefactors. They were not just silent ghosts haunting the young cosmos. They may have been the unseen architects of its illumination, using their gravity to sculpt the first brilliant structures out of the formless dark, setting the stage for the vibrant cosmic tapestry we see today. Now we turn our attention from the grand structure of galaxies to a specific and puzzling discrepancy in the chemical recipe of the cosmos itself. For decades, cosmologists have celebrated the remarkable success of Big Bang nucleosynthesis, the theory that describes how the first atomic nuclei were forged in the fiery first few minutes of the universe. The predicted abundances of the lightest elements, hydrogen, helium, and their isotopes match our observations of the oldest stars and distant gas clouds with stunning accuracy. It's a cornerstone of modern cosmology, but there is one glaring exception, a single ingredient that stubbornly refuses to fit the prediction: lithium. The oldest stars in our galaxy contain only about 1/3 to 1/2 of the lithium-7 that the standard models say should have been produced. This is the cosmological lithium problem, a nagging mystery that has persisted for over 30 years, and one intriguing solution points a finger directly at the evaporating remnants of primordial black holes. To understand how a black hole could influence the chemistry of the entire universe, we need to zoom in on that crucial first few minutes after the Big Bang. During this brief, searing hot period, the entire cosmos was a nuclear fusion reactor. Protons and neutrons collided and fused, first forming deuterium, then helium, and a very tiny trace amount of lithium-7, along with its isotope lithium-6. Then, as the universe expanded and cooled dramatically, the temperature dropped below the point where nuclear fusion could continue. The nuclear reactions effectively froze, locking in the primordial abundances of these elements. The problem is that when we look at the atmospheres of ancient stars, which are thought to preserve this primordial chemical makeup, the amount of lithium we measure is significantly lower than what the calculations tell us should be there. Something must have destroyed a portion of the lithium after it was created, but before these oldest stars formed. This is where the tiniest primordial black holes enter the stage. According to the Kerr-Hawking mass spectrum, the universe could have produced a vast number of PBHs with very low masses. These small black holes would have been incredibly hot due to Hawking radiation, causing them to evaporate on timescales of minutes, hours, or years after the Big Bang. Now consider what happens during that final, explosive evaporation. The black hole doesn't just emit a gentle glow of low-energy photons. It erupts in a burst of high-energy radiation, including a flood of protons, neutrons, and other particles. This shower of energetic particles is the key to the lithium problem. As these particles, particularly the protons, stream out into the surrounding primordial gas, they act like a cosmic shredder, capable of smashing into the newly formed lithium nuclei and breaking them apart. The process is known as spallation. A high-energy proton carrying a tremendous amount of kinetic energy from the black hole's explosion slams into a fragile lithium-7 nucleus. The collision doesn't fuse the nuclei, it shatters the lithium into smaller fragments, typically turning it into 2 helium nuclei or other lighter particles. It's a destructive rather than a creative nuclear process. For this theory to work, the timing and distribution of these evaporating black holes would have to be just right. They would need to be evaporating during the epoch after Big Bang. Nucleosynthesis had frozen, but before the first stars condensed and locked in the chemical abundances, a window that might have lasted for hundreds of millions of years. A population of PBHs evaporating throughout this period would have acted as a universal lithium-destroying factory, systematically reducing the overall abundance to the lower level we observe today. The elegance of this proposal is that it ties together 2 seemingly unrelated puzzles: the nature of dark matter candidates and a specific anomaly in elemental abundances. However, like any good scientific idea, it faces stringent tests. The same high-energy particles that destroy lithium would also interact with other elements in the primordial soup. For instance, they could produce extra deuterium or helium-3 through other spallation reactions. The challenge for theorists is to craft a model where the PBH population is dense enough to destroy the required amount of lithium, but not so dense that it overproduces these other elements, which would then create new discrepancies with the otherwise successful predictions of Big Bang nucleosynthesis. It's a delicate balancing act. Furthermore, the evaporation events would have injected a significant amount of entropy or disorder into the universe, potentially leaving other imprints on the cosmic microwave background. The fact that we see a nearly perfect blackbody spectrum places tight constraints on how much energy could have been dumped into the cosmos in this way, effectively ruling out some of the more extreme PBH models proposed to solve the lithium problem. So, does this theory elegantly solve the long-standing puzzle? The answer is that it remains a compelling, albeit unproven, possibility. It demonstrates the fascinating interconnectedness of cosmic phenomena, where the fate of the smallest nuclei could be dictated by the death throes of the most exotic gravitational objects. While other solutions to the lithium problem have been proposed, involving non-standard particle physics or nuances in nuclear reaction rates, the PBH hypothesis stands out for its creativity. It suggests that the missing lithium might not be a flaw in our understanding of nuclear physics, but rather a clue, a fossilized record of a dramatic and violent chapter in the very early universe, a time when the darkness of evaporating black holes subtly edited the first chemical elements into their final, observed form. Now, let's shift our perspective from the cosmic dawn to our own galactic neighborhood and consider a more intimate encounter. Imagine a primordial black hole, one of those ancient relics, not as a distant seed for a quasar or a component of dark matter, but as a solitary voyager passing right through our corner of the Milky Way. What would happen if one of these dark ghosts ventured into a region filled with the sparse gas and dust of the interstellar medium? The answer lies in a process that could make the invisible, however faintly, visible. This is the theory of PBH atmospheres and accretion, a hunt for the faintest glimmers in the dark. Even a black hole that is completely isolated and not part of a binary system is not truly alone in the void. Space is not a perfect vacuum. It's filled with a tenuous medium of primarily hydrogen gas with just a few atoms per cubic centimeter. For most objects, this density is so low it's negligible. But for a black hole, its gravitational pull is so intense that it can effectively sweep up this material as it moves. As the PBH travels through this diffuse gas, individual hydrogen atoms are captured by its gravity and begin to spiral inward. However, these particles rarely fall directly in. Because they have some angular momentum, they don't take a straight line plunge into the event horizon. Instead, they settle into a swirling, chaotic orbit, forming a structure known as an accretion disk. This is where the physics gets spectacular. As the gas spirals down toward the event horizon, it's compressed and heated to incredible temperatures through friction and gravitational energy conversion. The same process that powers brilliant quasars and X-ray binaries would occur around a wandering PBH, just on a vastly smaller and dimmer scale. For a stellar mass black hole, this can produce intense X-rays. But for a primordial black hole, the luminosity of this miniature accretion disk depends critically on its mass and its speed through the medium. A more massive PBH has a larger gravitational cross-section, allowing it to capture more material. A slower-moving one spends more time in a given cloud of gas, increasing its total intake. The resulting emission would primarily be in the form of high-energy X-rays, a faint, telltale glow against the blackness of space. This presents a tantalizing possibility for detection. Astronomers have catalogued countless X-ray sources across the sky, most of which are explained by known phenomena: active galactic nuclei, binary star systems where a compact object is feeding on a companion, or the hot remnants of supernova explosions. The search for a lone PBH, then, becomes a search for an anomaly, an isolated, point-like source of X-rays that has no visible optical counterpart. It would be an X-ray source that doesn't correspond to any star, any galaxy, or any other known object. Its light curve might be steady or irregular, but it would be fundamentally orphaned, a voice with no visible speaker. Searches for these ghostly X-ray emitters have been underway for decades, using space telescopes like Chandra, XMM Newton, and New Star. The challenge is immense, akin to searching for a single, faint firefly in a vast, dark field dotted with thousands of brilliant spotlights. The accretion luminosity of a typical asteroid mass PBH drifting peacefully through a standard region of the interstellar medium would be extraordinarily faint, likely below the detection threshold of all but the most sensitive, long-exposure observations. To have a realistic chance of being seen, a PBH would need to be experiencing a feast. If it were passing through an unusually dense molecular cloud, or if it were a more massive object, perhaps tens or hundreds of solar masses, the accretion rate would be higher and the resulting X-ray glow would be correspondingly brighter. So far, no unambiguously isolated X-ray source has been definitively identified as a primordial black hole, but this absence of evidence is itself a valuable result. It places upper limits on the number of such objects within a certain mass range that could be actively accreting at a detectable rate in our galaxy. It tells us that if they are out there, they are either too small, moving too fast, or in regions too empty to produce a noticeable signal with our current technology. Yet, the hunt continues to evolve. Future X-ray observatories with greater sensitivity and wider fields of view will scan the skies, and the analysis techniques are becoming more sophisticated, capable of sifting through vast datasets to find these tiniest of needles in the cosmic haystack. Discovering just one such source would be a monumental achievement, providing the first direct glimpse of an entity born from the turbulence of the universe's first second, caught in the act of quietly drawing its faint breath from the galaxy. We've already explored how cosmic defects like domain walls and cosmic strings could have kinked and snapped to form black holes, but one particular type of defect offers a remarkably precise and elegant formation mechanism that stands out for its mathematical beauty. This is the theory of primordial black holes born from the collapse of cosmic string loops. To visualize this, we need to picture cosmic strings not as static cracks in space-time, but as dynamic, vibrating entities. These hypothetical strings are thought to be incredibly thinner than a proton, yet unimaginably dense, with a single inch of string potentially weighing as much as a mountain range. In the chaotic aftermath of the Big Bang, a network of these strings would have formed, crisscrossing the young universe like a tangled web of infinitely strong spaghetti. As the universe expanded, this network would have evolved. Long, stretching strings would occasionally intersect and cross, sometimes snipping off closed loops. These loops are the key players here. Once a loop is severed from the main network, it doesn't just hang there motionless. Under its immense tension, it begins to oscillate wildly, whipping through space at relativistic speeds. Now, according to Einstein's equations, any concentration of mass and energy warps space-time and generates a gravitational field. An oscillating loop of cosmic string, with its extraordinary mass-energy density, creates a powerful, oscillating gravitational field. As the loop vibrates, it loses energy by radiating gravitational waves, causing it to gradually shrink in size. This leads to a critical threshold. If the loop is oscillating in a particularly efficient way specifically, if it has a certain number of peaks and troughs or cusps, where its velocity momentarily becomes incredibly close to the speed of light, the concentration of energy at those points can become so extreme that the loop's own gravity becomes insurmountable. When this happens, the loop doesn't just keep shrinking, it undergoes a catastrophic gravitational collapse. The entire mass energy of the loop, which might be equivalent to many solar masses, collapses directly into a black hole. It's a direct and clean conversion. One exotic object, the cosmic string loop, transforms into another, a primordial black hole, in a single, violent event. What makes this theory so powerful is its predictive specificity. The mass of the resulting black hole isn't random. It is directly proportional to the length of the cosmic string loop at the moment it collapses. Since the loop's length is determined by the properties of the cosmic string itself, primarily its tension, a fundamental parameter, this theory predicts a distinct mass distribution for the resulting PBHs. Unlike the broad spectrum possible from direct collapse of density fluctuations, cosmic string loops would produce black holes with masses that are multiples of a fundamental unit set by the string's tension. This means if we were to one day discover a population of black holes with a very specific characteristic mass distribution, it could serve as a direct fingerprint of cosmic strings, offering evidence not just for primordial black holes, but for a fundamental aspect of particle physics that has so far remained in the realm of theory. This creates a fascinating bridge between the microscopic world of high-energy physics and the macroscopic scale of astrophysics. The existence and properties of cosmic strings are predicted by many grand unified theories, which attempt to describe how the fundamental forces were once merged. Therefore, discovering a PBH with a mass that fits the cosmic string loop prediction would be a double victory. It would confirm the existence of these ancient gravitational fossils while simultaneously providing the first concrete evidence for cosmic strings, thus validating a major class of theories about the universe's very first moments. It transforms the search for black holes into a direct probe of physics at energy scales far beyond what any particle collider on Earth could ever hope to achieve. But what if some galaxies never manage to light up at all? This leads us to a concept that pushes the boundaries of what we even define as a galaxy. Imagine a vast, coherent structure weighing as much as a small galaxy like the Small Magellanic Cloud, held together by gravity and orbiting within a galaxy cluster. Now imagine that almost all of that mass is locked away in a swirling population of primordial black holes, with only a handful of actual stars sprinkled throughout. This is the theory of the PBH dark galaxy, a structure where the dark matter isn't a smooth, mysterious halo, but is instead composed of discrete, ancient black holes that simply never triggered significant star formation. The formation of such an object would be a story of gravitational segregation. In the early universe, as dark matter began to collapse into the first protogalactic halos, a region that happened to have an overabundance of primordial black holes would have a very different destiny. While ordinary dark matter particles, if they exist, form a diffuse halo, a swarm of PBHs behaves more like a collisionless gas of massive objects. Their collective gravity would be intense and clumpy from the start. As this dark swarm condensed, it would have begun to pull in the ordinary hydrogen and helium gas from its surroundings. However, here's the critical twist. The very nature of the PBH swarm might prevent that gas from ever cooling and collapsing into stars. The gravitational interactions within the swarm would be chaotic, stirring up the infalling gas and keeping it too hot and turbulent to settle into the dense, cool clouds required for star birth. Furthermore, without a single, massive central black hole to act as a stabilizing anchor and trigger organized accretion, the gas might simply bounce around in the chaotic gravitational field of the swarm, never finding a calm center where it can condense. The result is a galaxy-sized mass that failed to become a galaxy in the traditional sense, a dark metropolis with no lights on. The observational signature of such a dark galaxy would be as elusive as it is fascinating. It would be virtually invisible across almost the entire electromagnetic spectrum. With no bright stars, it wouldn't emit visible light. With little to no star formation, there would be no hot, young stars to produce ultraviolet radiation or to heat surrounding dust to emit infrared light. What you would have is an enormous amount of mass that reveals itself only through its gravitational influence. The most promising way to detect it would be through gravitational lensing. If a dark galaxy drifted in front of a more distant, bright galaxy or quasar, its combined gravitational pull would warp the spacetime around it, creating characteristic distortions in the background source's image. Instead of the clean, dramatic arcs produced by a massive galaxy cluster, a dark galaxy might produce a more complex, speckled pattern of micro-lensing events, a subtle shimmering effect as individual black holes in the swarm passed in front of different parts of the background source. It would be like trying to see a ghost by watching how it distorts the view of a street lamp behind it. This theory offers a potential explanation for one of the more puzzling discoveries in recent astronomy, ultra-diffuse galaxies or UJ. These are galaxies that have the spatial extent of large galaxies like the Milky Way but contain only about 1% of the stars. They are ghostly, see-through objects. While many UDGs can be explained by processes like tidal stripping or failed accretion, some appear to be incredibly rich in dark matter, with mass-to-light ratios that are extraordinarily high. Could it be that the dark matter in these strange galaxies is not a smooth particle halo, but is actually a dense swarm of primordial black holes? The PBH model could naturally account for both the high total mass and the failure to form stars. The chaotic gravitational environment of the swarm would suppress star formation from the beginning, leaving the galaxy permanently diffuse and dark. Finding a UDG with gravitational lensing properties that suggest a clumpy, rather than smooth, dark matter distribution would be a thrilling hint that we may have already stumbled upon one of these shadowy realms, a galaxy built not from stars and dust, but from the concentrated darkness of the universe's first moments. While the idea of primordial black holes solving the dark matter puzzle is elegant, it forces us to confront one of the most fundamental debates in all of modern physics. Is our understanding of gravity itself incomplete? This brings us to a radical alternative that seeks to explain the universe without any dark matter at all, a theory known as modified Newtonian dynamics, or MND. At its heart, MND proposes a simple but profound adjustment to Newton's laws of motion, suggesting that gravity behaves differently at the extremely low accelerations found in the outskirts of galaxies. Instead of invoking vast amounts of invisible matter to explain why stars orbit galaxies faster than expected, MND suggests that our equations for gravity are simply wrong in this weak field limit. The appeal is undeniable. It removes the need for a mysterious, undiscovered particle and instead attributes the observed effects to a modification of a well-known force. For decades, MND has been a compelling, if controversial, challenger to the dark matter paradigm. This is where primordial black holes create a fascinating philosophical crossroads. If we were to discover that PBHs do indeed constitute the dark matter, it would be a resounding victory for the standard model of cosmology. It would mean that dark matter isn't a smooth, exotic particle but a tangible, albeit dark, astrophysical object. This would squarely contradict the central premise of MND, which is that no form of dark matter is necessary. The gravitational effects of a PBH swarm would be indistinguishable from those of any other form of dark matter on galactic scales. They would provide the extra gravitational pull that MND seeks to explain away through modified physics. A confirmed detection of PBHs as dark matter would therefore seem to sound a death knell for MND, firmly re-establishing Einstein and Newton's gravity as correct and closing the book on this particular alternative. However, the relationship is not quite so simple, and the story takes an intriguing turn. The success of MND in predicting galactic rotation curves is its greatest strength, but the theory has faced significant challenges when applied to the largest scales of the universe, particularly the dynamics of entire galaxy clusters and the features we see in the cosmic microwave background. To explain these observations, even the most ardent MND proponents often have to invoke some form of missing mass, perhaps in the form of neutrinos with a small mass or other non-dark matter particles. This is where a population of primordial black holes could, paradoxically, find an unexpected home within a modified gravity framework. If MND requires a small amount of additional, conventional mass to work on the largest scales, PBHs could potentially serve that role. They would not be the dominant form of mass in the universe as in the standard dark matter model, but rather a secondary component that helps reconcile MND with cluster and cosmological data. In this hybrid scenario, PBHs wouldn't be the dark matter. They would be a separate, visible, or rather gravitationally detectable, form of ordinary mass that helps complete the MND picture. This potential for a hybrid model places primordial black holes at the very center of a fundamental tug of war in physics. Their discovery would not immediately end the debate. Instead, it would force both sides to refine their arguments. For dark matter theorists, the challenge would be to show that a PBH-based model can replicate all the successes of MND on galactic scales. particularly the precise relationships between a galaxy's visible mass and its rotation curve, which Mann predicts with remarkable accuracy. For Mann supporters, the challenge would be to determine if and how a specific population of PBHs could be integrated into their models without undermining the theory's elegant simplicity. The gravitational signatures of PBHs, especially if they are found to cluster in specific ways within galaxy halos, could provide a crucial test. A smooth dark matter halo might be mimicked by a modification of gravity, but the subtle, clumpy gravitational effects of a swarm of discrete black holes could produce unique signatures that neither pure Mann nor standard particle dark matter can easily explain. The hunt for primordial black holes, therefore, becomes more than just a search for an ancient relic. It transforms into a direct experiment that could adjudicate between two competing visions of reality, determining whether the cosmos is filled with dark objects or governed by dark rules. Now we push the boundaries of physics into a realm where the universe has more than the three spatial dimensions we experience every day. This is not just science fiction, it's a serious proposition from advanced theories like string theory, which attempt to unify gravity with the other fundamental forces. These models suggest that our reality is like a four-dimensional membrane or brain floating within a higher dimensional space, often called the bulk. And this exotic framework leads us to a theory about primordial black hole formation that is perhaps the most radical of all, one where the strength of gravity itself was fundamentally different in the universe's first moments. To grasp why this changes everything, we need to understand a fundamental puzzle in physics known as the hierarchy problem. In our familiar three dimensions of space, gravity is astonishingly weak compared to the other forces. A tiny fridge magnet can overcome the gravitational pull of the entire Earth. Why is there such a vast difference in strength? One compelling idea from theories with extra dimensions is that gravity only appears weak to us because it is not confined to our three-dimensional brain. It can spread out or leak into these additional compactified dimensions. Imagine gravity as a ripple on the surface of a pond. In three dimensions, the ripple spreads out and weakens rapidly. But if the pond were actually a very thin, narrow channel, the ripple would be much more concentrated and powerful. In the same way, if the true scale of gravity is set in these higher dimensions, it could be intrinsically much stronger than we perceive it to be in our limited, three-dimensional slice of reality. This leads to a staggering consequence for the very early universe. If we rewind time to just after the Big Bang, when all dimensions were believed to be compact and unified, the effective strength of gravity would have been exponentially more powerful. The energy required to warp spacetime enough to create a black hole, the Planck energy, would have been dramatically lower. In our three-dimensional world, forming a black hole requires concentrating a star's worth of mass into a tiny volume. But in a universe where gravity operates with its full, undiluted strength in higher dimensions, the threshold for black hole formation plummets. Cataclysmic particle collisions that would be commonplace in the high-energy early universe, which in our dimensions would simply produce a shower of particles, could have instead routinely curved space so severely that they pinched off microscopic black holes. The production of black holes could have been not a rare event, but a prolific, factory-like process. This theory provides a breathtakingly elegant mechanism for flooding the cosmos with primordial black holes. Instead of relying on specific, finely tuned density fluctuations or cosmic defects, black hole production becomes a natural and abundant outcome of the high-energy particle physics occurring when the universe was a fraction of a second old. Every region of space seething with energy could have been a potential birthplace. The black holes formed in this way would have been truly microscopic, perhaps with masses not much larger than a speck of dust, but they would have been created in incomprehensible numbers. As the universe expanded and cooled, the extra dimensions would have compactified, and gravity would have taken on the weak character we know today, but the legacy would remain. a vast sea of these tiny gravitational relics left over from an era when the fundamental laws of physics played out on a higher dimensional stage. The connection to dark matter then becomes almost inevitable. This prolific production mechanism could easily have manufactured enough microscopic black holes to account for the entire dark matter content of the universe. Their collective gravitational pull would perfectly explain the dynamics of galaxies and clusters, just as particle dark matter does. But this theory offers a unique signature. Because these PBHs would form from particle collisions, their initial mass distribution might carry a specific imprint, different from the spectrum predicted by other formation theories. Furthermore, if they were created in such abundance, their eventual evaporation through Hawking radiation could have left a distinct mark on the cosmic background radiation or the abundance of light elements. This creates a direct, testable link between the geometry of the universe's hidden dimensions and the observable astrophysics of the present day. It suggests that the solution to the dark matter mystery might not be found in a new particle, but in a new understanding of space itself, and that the invisible fabric of the cosmos is woven not just from 3 dimensions, but from many, with the first black holes as permanent knots in that hidden geometry. Now we turn our attention to one of the most enigmatic signals in the modern cosmos, a phenomenon that has puzzled astronomers since its discovery: fast radio bursts. These are not gentle whispers from space, but sudden, colossal shrieks of radio energy. In a mere thousandth of a second, an FRB can release more energy than our Sun emits over several days. They arrive from deep space, often from other galaxies, and while some repeat, most are one-off events, flashing into existence and vanishing just as quickly. The hunt for their origin has produced a host of suspects, from flaring magnetars to merging neutron stars. But what if the answer lies not with the death throes of stars, but with the silent passage of something far older and darker? This is the speculative but fascinating theory that primordial black holes could be the hidden engines behind some of these brilliant, fleeting bursts. To understand how a dark, silent object could produce such a brilliant flash, we need to consider the environments it might pass through. One of the most compelling scenarios involves a primordial black hole on a chance encounter with one of the most magnetically charged objects in the universe, a neutron star. A neutron star, especially a pulsar, is a cosmic powerhouse with a magnetic field trillions of times stronger than Earth's. This field extends far out into space, creating a vast, structured region known as a magnetosphere. Now imagine a mountain-mass primordial black hole drifting innocently through the void, its path taking it straight through this intense magnetic bubble. As the PBH moves, it acts as a conductive body, disturbing the magnetic field lines. Think of it like dragging a stone through a still pond. The water ripples and churns. In the magnetosphere, this disturbance can trigger a phenomenon known as magnetic reconnection. The stressed field lines snap and reconfigure themselves, a process that releases a tremendous amount of stored magnetic energy in a violent burst. This sudden release of energy could be channeled into a focused beam of radio waves, shooting out from the poles of the neutron star and appearing to us as a fast radio burst. Another, even more direct mechanism ties back to the final fate of the smallest primordial black holes. As we've discussed, a low-mass PBH emits Hawking radiation and eventually evaporates in a tremendous burst of particles. This final explosion is a fireball of high-energy physics. The intense burst of radiation and plasma could itself generate a powerful shock wave that, when expanding into the surrounding interstellar medium, might produce a coherent blast of radio emission. The timing is key here. The entire evaporation event is incredibly brief, matching the millisecond duration of an FRB. If a significant population of these small black holes were reaching the end of their lives across the cosmos, their final explosive flashes could appear as a background of non-repeating FRBs, each one a dying shout from a black hole that had persisted since the beginning of time. Assessing the plausibility of these ideas requires comparing them to the detailed properties we've observed in FRBs. The theory faces some significant hurdles. For the neutron-star interaction model, a major challenge is energetics. The energy required to power a typical FRB is staggering. For a PBH to trigger a release of that much energy simply by passing through a magnetosphere, the interaction would likely need to be extraordinarily efficient, or the black hole itself would need to possess specific properties like a strong electric charge, which is considered unlikely. Furthermore, if this were a common mechanism, we might expect to see FRBs associated with known neutron stars in our own galaxy. But so far, the only confirmed galactic FRB was linked to a magnetar's own intense activity, not an external trigger. The evaporation model, while elegant in its simplicity, also runs into difficulties with the observed FRB signal. The radio burst from an evaporating black hole would likely be accompanied by a tremendous flash of gamma rays and other high-energy particles. While some FRBs have been found to have faint X-ray counterparts, a widespread correlated gamma-ray signal has not been detected, which places strong constraints on how often this could be happening. Moreover, the distribution of FRBs across the sky seems to trace the general distribution of matter in the universe, suggesting they are related to galaxies and stellar processes. A population of evaporating PBHs, if they are a component of dark matter, would be distributed throughout the galactic halo and in intergalactic space, which might produce a different statistical pattern than what we observe. So, what observations could potentially resurrect this theory or finally lay it to rest? The key will be in finding a smoking gun, a unique signature that distinguishes a PBH-generated FRB from one caused by more conventional astrophysics. If the neutron-star interaction model is correct, we might one day detect an FRB from a known pulsar, but with a signal profile that is impossible to explain by the star's own rotation or internal activity. The burst would have to be far more energetic than any known pulsar flare and would need to occur without any other change in the star's regular pulse. For the evaporation model, the discovery of a true, isolated FRB1 that occurs in a region of complete emptiness far from any visible galaxy would be a major point in its favor. The next generation of radio telescopes, like the Square Kilometre Array, will have the sensitivity to precisely localize thousands of FRBs. If a significant fraction of them are found to originate in the deep voids between galaxies, where stellar objects are exceedingly rare, the case for an exotic origin like primordial black holes would become much stronger. Until then, the theory remains a captivating example of how the most mysterious phenomena in the universe push us to consider the most extraordinary explanations, connecting the fleeting radio whispers of today to the ancient darkness of the first second. But the final moments of an evaporating primordial black hole hold a secret even more profound than a simple burst of energy. The Hawking radiation that spells its doom isn't just a random spray of particles, it's theorized to be a perfect thermal spectrum. This means the black hole, in its last desperate effort to shed mass, should act as an equal opportunity creator, producing particles and their antiparticles in perfectly balanced pairs. Electrons and positrons, protons and antiprotons. The dying black hole becomes a factory for matter and its ghostly mirror image. This raises a staggering possibility. Could the final explosions of these ancient objects be a significant, ongoing source of antimatter throughout our galaxy? Antimatter is one of the universe's great mysteries. When a particle of matter meets its antimatter counterpart, they annihilate each other in a flash of pure energy, primarily in the form of gamma rays. We know antimatter exists. We can create tiny amounts of it in particle accelerators. But when we look out at the cosmos, the universe appears to be almost entirely made of matter. The profound question of why there is such a dramatic imbalance, why there was any matter left over after the Big Bang to form stars and planets and us, remains one of the biggest unsolved problems in physics. If the early universe created matter and antimatter in equal amounts, they should have completely annihilated, leaving behind a sea of radiation and nothing else. Something must have tipped the scales. While primordial black holes didn't cause the initial imbalance, they could be a secondary source, continuously injecting fresh antimatter into the galaxy. Imagine a population of small PBHs sprinkled throughout the Milky Way's dark matter halo, each one ticking like a clock toward its final evaporation date. As one reaches the end of its life, it doesn't just vanish, it spews out a cloud of newly created particles, with antimatter making up half of that cloud. This antimatter wouldn't last long. The positrons and antiprotons would immediately encounter the ordinary matter of the interstellar medium, the sparse hydrogen gas that fills the space between stars. The resulting annihilations would produce a very specific signal, a sharp spike of gamma rays at a characteristic energy of 511,000 electron volts, which is the fingerprint of an electron and a positron meeting their end. This gives astronomers a specific and powerful way to hunt for these dying black holes. By scanning the sky with gamma-ray telescopes like the Fermi Gamma-Ray Space Telescope and searching for these distinct annihilation lines, we could potentially pinpoint the location of a recent PBH death. The challenge, of course, is the signal's brevity and intensity. The final evaporation is incredibly fast, and the resulting annihilation flash would be a brief, localized event. We wouldn't be looking for a steady glow, but for a sudden, sharp burst of gamma rays at a very specific energy, a ghostly flare that appears and then fades from a point in the sky where no other astrophysical source is visible. It would be the ultimate cosmic signature, the death cry of a black hole, echoed by the silent flash of matter and antimatter meeting in mutual destruction. However, turning this elegant idea into a confirmed detection faces significant hurdles. The galactic interstellar medium is not a perfect vacuum, but it is extremely diffuse. The antimatter particles created in the explosion would have a high velocity and could travel a considerable distance before they finally encounter a regular matter particle to annihilate with. This means the gamma-ray signal might be smeared out over time and space, making it more difficult to distinguish from the general background gamma-ray noise of the galaxy. Furthermore, other astrophysical processes, such as certain types of high-energy interactions around pulsars, can also produce antimatter and similar gamma-ray signatures. To confidently attribute an observation to a PBH, we would need to rule out all other possible explanations, requiring a level of precision in our measurements that is only now becoming possible. Despite these challenges, the search continues because finding such a signal would do more than just confirm the existence of primordial black holes. It would reveal a hidden antimatter engine operating in the dark corners of our galaxy, a remnant of the universe's violent birth still subtly shaping its chemical makeup billions of years later. We have journeyed through a landscape of incredible theories, from cosmic strings to baby universes, but all these ideas share one fundamental need: definitive proof. The hunt for primordial black holes is accelerating from speculative theory into a hard-nosed observational science, and the next decade promises to be a golden age, powered by a new generation of telescopes and techniques that will push the boundaries of what we can see. We are no longer just imagining these dark relics, we are building the tools to find them. At the forefront of this effort is an observatory that has already begun to reshape our view of the cosmic dawn, the James Webb Space Telescope. While JWST wasn't designed to detect black holes directly, its profound ability to peer back in time to the very first galaxies provides a crucial indirect test. By studying the properties of these ancient galaxies, their sizes, masses, and how quickly they formed, JWST offers a powerful way to constrain the existence of those massive primordial seeds. If we consistently find supermassive black holes in galaxies that are too young to have grown them by standard accretion, the case for pre-existing heavy seeds becomes overwhelming. JWST is effectively conducting a census of the infant universe, and every fully formed giant black hole it finds in a toddler galaxy is a strong, albeit circumstantial, piece of evidence pointing toward a primordial origin. But to move from compelling hints to direct confirmation, we need to sense the black holes themselves, and that requires listening to the universe in a completely different way. This is the revolutionary promise of the Laser Interferometer Space Antenna, or LISA. Scheduled for launch in the next decade, LISA will be the first gravitational wave observatory in space, consisting of 3 spacecraft flying in a perfect triangle millions of kilometers apart. Unlike ground-based detectors like LIGO and Virgo, which are sensitive to the high-frequency chirps of stellar mass black holes merging, LISA will open a new window on the low-frequency rumble of the cosmos. This is the domain of the supermassive and intermediate mass black holes. LISA will be able to hear the mergers of black holes weighing thousands to millions of solar masses, collisions that would have taken place when the universe was young. If primordial black holes in this intermediate mass range are common, LISA should detect a cosmic chorus of their mergers. The frequency, masses, and locations of these events would provide a direct census. A high rate of mergers in the early universe, especially between black holes that appear to have formed in isolation, would be a signature that is incredibly difficult to explain without a primordial population. LISA won't just be listening for black holes, it will be listening to the formation history of the black holes themselves. Back on the ground, another monumental project is preparing to scan the heavens with unprecedented speed and depth. The Vera C. Rubin Observatory, with its immense 3.2 gigapixel camera, will embark on a 10-year survey of the entire southern sky. Its core mission includes a massive, automated search for gravitational microlensing events. By monitoring billions of stars night after night, the observatory will be able to detect the subtle, transient brightening caused by dark, compact objects including primordial black holes, passing in front of distant stars. The sheer volume of data from Rubin will be transformative. While previous microlensing surveys have placed tight constraints on PBHs as dark matter, Rubin's incredible sensitivity and panoramic view will allow us to probe mass ranges with far greater precision. It could detect a population of Earth mass or Neptune mass black holes that have so far eluded detection, or it could conclusively rule them out. Furthermore, by measuring the duration and shape of millions of microlensing events, Rubin might even identify the unique signature of a binary primordial black hole system, adding another layer of evidence to the hunt. This relentless, automated stare into the cosmos will turn the subtle art of microlensing into a robust statistical science. The future, however, extends beyond these flagship missions. Advanced X-ray observatories will scan the galaxy for the faint, isolated glow of a solitary black hole accreting wispy interstellar gas. Next-generation cosmic microwave background experiments will measure the faintest spectral distortions with even greater precision, searching for the energy imprint of evaporating black holes. And neutrino observatories will listen for the unique signal of a black hole dying or colliding with a neutron star. We are entering an era of multi-messenger astronomy where we won't rely on a single method. A potential discovery might involve LISA detecting the merger of an intermediate mass black hole binary, while the Vera Rubin Observatory simultaneously records a microlensing event from a similar mass object in our own galaxy, and James Webb data confirms the early existence of such behemoths. This convergence of evidence from independent techniques would be the smoking gun, the undeniable proof that these ancient phantoms are real. We stand at the threshold of a potential revolution where the dark, silent architects of the cosmos may finally be revealed, rewriting not just the story of the universe's first black holes, but the very first chapter of everything. And so our journey through the cosmic shadows reaches its end for now. We have ventured from the unimaginable heat of the Big Bang's first moments, where raw energy might have collapsed directly into black holes, to the violent collisions of inflationary bubbles and the snapping of cosmic defects in the newborn universe. We've considered the possibility that these ancient entities are the invisible dark matter binding galaxies together, and that they served as massive seeds, giving supermassive black holes a head start in a race against time. We've explored their potential to evaporate in a flash of Hawking radiation, to collide and send ripples through space-time, and even to secretly orbit our sun as phantom planets. From the profound implications of Planck stars and baby universes to the speculative links with fast radio bursts and the antimatter mystery, the range of ideas is as vast as the cosmos itself. What emerges is a picture of incredible diversity, where the label primordial black hole could apply to a microscopic quantum speck or a colossal giant, each born from a different cataclysm in the fiery dawn of everything. The search for these objects is far more than a niche pursuit. It is a fundamental inquiry that connects the largest scales of galaxy formation to the smallest scales of quantum gravity, tying together cosmology, particle physics, and astronomy into a single grand quest. It forces us to question the very nature of space-time, matter, and the origins of the cosmic structures we see today. The hunt is accelerating, driven by powerful new tools like the James Webb Space Telescope, the future LISA Observatory, and the Vera Rubin Observatory, each offering a new way to probe the darkness. We stand on the brink of discoveries that could reshape our understanding of the universe's first chapter, so we turn the question over to you. With 30 compelling theories on the table, which one captures your imagination the most? Do you believe dark matter is a swarm of ancient black holes, or that our universe was born inside one? Let us know in the comments below, and don't forget to subscribe for more deep dives into the mysteries of the cosmos.